ご来場の皆様にご案内申し上げます。本日
I'd like to give an announcement to the participants at the venue. Thank you very much for your participation in the annual Symposium 2023 on the ITER activities. We will be starting the annual symposium shortly. Before the start of the symposium, we'd like to make some housekeeping announcements. Participants at the venue, at the lobby, please come into the hall and have a seat. If you are not feeling well, please stay away from attending today's symposium. Please have a seat designated for you and do not use other seats. If you are not sure about where your seats are located, please ask the staff close to you. Except for people related, you are not allowed to see the symposium while standing. And also, except for people related and stakeholders, you are not allowed to do streaming and recording of the video and audio. If you have cell phones and smartphones, please turn off the power or switch it to silent mode in advance. Eating, drinking, and smoking are not allowed in the hall. If you'd like to have something, please do so at the hall lobby or hall foyer at the back side of the venue seat. We have the smoking room on the fourth and the first floor. In case of emergency, such as earthquakes and disasters, please stay seated until the staff makes some announcements and give instruction. Please wait for a while before the symposium will start. Good afternoon, ladies and gentlemen. Thank you very much for your participation in the annual Symposium 2023 on the ITER BA activities, A Sustainable Future, opened up by fusion energy. My name is Mio Nakamoto, the Master of Ceremony today from National Institute for Quantum Science and Technology, OQST. I research and develop plasma measurement with ITER optical equipment at Nanka Fusion Institute. Thank you very much for having me today. First, on behalf of the host, we'd like to invite Professor Sawataka Mitsu, Chairperson of the Fusion Energy Forum. As Chairperson of the Fusion Energy Forum of Japan, or FEEJ, I would like to express my sincere gratitude for your participation from various and different fields despite your busy schedule. The FEEJ hosting the symposium was founded in July 2007 to support research and development to realize nuclear fusion, consisting of experts from various fields, as well as many voluntary members agreeing to the objective. From FY 2020 to last fiscal year, we limited the number of seats within the hall, considering the pandemic situation. This year, fortunately, we are delighted to host and hold the annual symposium without any seat restrictions for the first time in 4 years. Her Excellency Ms. Sanae Takaichi, Minister in charge of Science and Technology Policy, reported on December 26th last year that the new organization on nuclear fusion involving the private sector, government, and academia to be launched by the end of this fiscal year received registration for participation requested by about 50 companies from various industries such as communications, trading, and finance. Nuclear fusion is described to become decarbonized power in 30 years from now, and it was also said so in the past as well. Why has it been always 30 years from now and in the past? This is because nuclear fusion has not been truly needed, at least up until now. However, recently, many nuclear fusion-related startups have been launched simultaneously in the United States, China, EU countries, India, Russia, and Japan, enhancing the expectation for nuclear fusion power generation. In other words, nuclear fusion has been now regarded as one of the decarbonized power options in addition to nuclear and renewable energy. However, perhaps experts and professors do not have an answer to the question of when nuclear fusion power generation, called the Sun on Earth, will be practically used after sound market competition between startups and proper support from the government. I'd like to share my view as an economist. For nuclear fusion to be truly needed and be used in practice, at least there should be two things. First, conviction that power demand will surge in the future. Second, confirmation that the cost of nuclear fusion power generation will be sufficiently lowered. Then, how will power demand change in 10 years and in 20 years? The population decline, power saving of electric devices, and less frequent migration of people will surely decrease the demand for power. On the other hand, as self-driving cars and artificial intelligence are used more in practice, we need to build more data centers which consume a great amount of power. Self-driving cars will drive safely by exchanging data with data centers, not by mounting advanced computers in each car. Each fully autonomous car would consume as much power as does a standard household. There are also many uncertainties. To what extent widespread use of AI will increase power demand? How widely self-driving cars will spread? And whether it will be possible to build data centers in countries with lower power cost, such as Canada, Iceland, and Norway. Therefore, precise analysis and forecast will be needed on how domestic power demand will change in the future. Nuclear fusion will incur prohibitively high cost at the initial stage, but as the technology comes closer to completion, R&D will focus more on how we can reduce the cost. I sincerely hope that young researchers will be dedicating themselves to study to reduce the cost of nuclear fusion power generation comparable to light water reactors and renewables. I'd like to conclude my opening remarks by hoping that the research will be further promoted to make a breakthrough in nuclear fusion. Wishing all the young researchers a good luck. Thank you for your attention. Thank you very much.
Now, we would like to ask the distinguished guests to give us a few words despite their busy schedules. And first of all, from the Ministry of Education, Culture, Sports, Science, Technology, Mr. State Minister, Mr. Imaeda, please take the stage. Again, good afternoon, ladies and gentlemen. And thank you for your introduction. I am the State Minister of Education, Culture, Sports, and Science Technology. And first of all, I would like to offer my deepest condolences to our deeply affected by the earthquake in Noto and also to the bereaved family. Please accept my deepest condolences. And those who are in shelter or those victims, I would like to deeply again offer my condolences. And upon the commencement of the symposium, I would like to say a few words, and I would like to express my sincere appreciation and to Mr. Mori and Chairman of committee, and thank you very much. And Mr. Sawa, thank you very much for your effort to put this together, and also Nuclear Fusion Forum and the parliamentarians, academia, and the industry, and those who are here, everyone here. And I would like to offer my deepest, express my sincere appreciation. And recently, climate change has become more serious around the world, and Japan has been working diligently to achieve carbon neutrality by 2050. And fusion energy plays an extremely important role in addressing this critical issue. And major countries are accelerating international competition by formulating national strategy and establishing venture companies. In April last year, Japan's first national strategy, the Fusion Energy Innovation Strategy, was formulated. In December of last year, Prime Minister Kishida announced that the government of Japan would make the most of the accelerate its effort toward early realization of fusion energy, including collaboration with industry in consideration of safety regulations, by making maximum use of technology and human resources cultivated through ITER project and others projects. So our minister next is working to strengthen research and development in the private sector, including startups. Universities reinforce support measures for creating emerging technology and study safety regulation. Today, our theme, the ITER project, and we are working together with to establish community. That today's theme, the ITER project MBA activities serve as extremely vital role in the early materialization of fusion energy. In the ITER project, the superconducting coils manufactured in Japan and other equipment manufactured by various players have been delivered and now currently being assembled. We expect that this project will be propelled steadily under the leadership of Mr. Balbasky, Director General of ITER, and Mr. Kamada, the Deputy Director of ITER. And in October last year, Mr. Balbasky visited Mr. Tokura, and we accompanied from industry through this visit, we communicated the need of fusion energy to the industry, and we were very much encouraged. And we visited the site, and I encourage you to visit the site as well. And on the VA activities, under the collaboration with the government of Japan and Europe in Ibaraki, Naga City, the largest experiment, JT60SA, achieved production of the plasma for the first time. In December last year, the grand commemorative ceremony was held to celebrate the start of operation. In Rokasho Village, Aomori Prefecture, each project is making solid progress, including formation of International Fusion Research and Development Center. So we are seeing solid progress. The minister will continue to support this project with full of dreams and hopes for the future of strongly promote research and development and human resource development. And I hope that students and young researchers and engineers who are participating today will join us in this project and endeavor together will pave the way to a future filled with hope. And finally, I would like to wish the success of this forum. Thank you very much for your attention. Mr. State Minister, thank you very much.
Now, I would like to ask a few words from Mr. Ace Gemali, Chairperson, the League of Diet Members for Fusion Energy Promotion, Member of House of Representatives. Mr. Mali, please. Thank you for the introduction. My name is Ace Gemali, Chairperson of the League of Diet Members for Fusion Energy Promotion. It is I would like with Mr. Akinori as member of the House of Representatives. I am in present today, and thank you very much for your condolence from the Vice Minister for the Noto, earthquake in Noto, and I would like to send my condolences as well. And I am really pleased that so many guests are here with this venue and the forum, and I am also feeling privileged to be present here. The parliamentary group that I chair has been active for 40 years. I remember at times there were heated bidding war between Japan and Europe when it came to selecting the site for ITER. And I just became a member of the. I just became a policymaker at the time, and I really strive for the selection. But In the end, we decided to build ITER in Europe. At the same time, we decided to work on broad approach activities jointly by Japan and Europe. And as a part of this, we made a decision to build JT60SA in Japan. The most important projects for the realization of fusion energy are the ITER project and the broader approach activities, which are the subject of today's discussion. The ITER project is a symbolic international project promoted by 35 countries in 7 major regions of the world. Currently, under the leadership of ITER Director General Dr. Barabasuki and Deputy Director General Dr. Kamada, the project is progressing with the support of many Japanese stakeholders. The broader approach activities hosted by Japan have been going on successfully through international cooperation with Europe, as well as with local support in Rokasho Village in Aomori Prefecture and Naka City in Ibaraki Prefecture. In October last year, JT60SA at the Naka Research Institute achieved its first plasma, and the ceremony to commemorate the start of the operation took place in December with the presence of Mr. Barabasuki. I attended the ceremony. I was very pleased to see the achievement of the first plasma. A great deal of effort was invested in this achievement. I would like to thank everyone involved for their hard work and dedication. I hope that many of the findings obtained here will be applied to the ITER project and the demo class reactor, contributing to the success of this project and to the early realization of fusion energy. For the early realization of fusion energy, we need to strongly promote the ITER project and broad approach activities to develop demo. It is also important to promote the multifaceted approach, including the development of emerging technologies such as miniaturization and sophistication, nurturing human talent, efforts toward industrialization, and strategic promotion of international activities. I believe that with concerted effort among everyone involved, the ITER project and the broad approach activities will lead to a success. We, the League of Diet members for Fusion Energy Promotion, promise to continue to provide firm support in cooperation with the government. I would like to conclude my remarks by thanking Dr. Takamisawa and all the members of the Fusion Energy Forum for their support in organizing this conference. Thank you very much. Thank you once again. Mr. Mori, thank you very much.
して日本経済団体で
Next, we would like to invite Mr. Izumisawa Seiji, Japan Business Federation Vice Chair, Chairman of the Committee on Mutsu Okawara Development, President and CEO of Mitsubishi Heavy Industries. The floor is yours. Good afternoon, everyone. Thank you for introduction. My name is Izumisawa from Mitsubishi Heavy Industries. I serve as chairman of the Committee on Mutsu Okawara Development in Keidanren, or Japan Business Federation. Before giving my remarks, I'd like to express my heartfelt condolences to the victims of the 2024 Noto Peninsula earthquake, which occurred January 1st, and extend my deepest sympathies to those who are affected. I'm in charge of the development and promotion of Mutsu Okawara Development Area, where QSD's Rokasho Fusion Institute is located. As a person from the business community, I'd like to give some remarks. First, I'd like to express my congratulations on the annual Symposium 2023 on the ITER activities. The importance of security and stable supply of energy has been reconfirmed globally against the backdrop of Russia's invasion on Ukraine and continued uncertainty in procurement of resources. To ensure stable supply of energy at low price and realize carbon neutrality at the same time, green transformation, called GX, will be essential as a transformation of the entire economy and society Keidan-ren, under the leadership of Chairman Tokura, came up with recommendations for green transformation in last May. Mr. Tokura participated in GX Implementation Council set up by the government following the recommendations, which established the basic policy for the realization of GX in line with Keidan-ren's recommendations. Based on that, the cabinet decided on the GX promotion strategy last July, under which Japan's nuclear fusion policy is entering the execution phase. It is important to steadily proceed with the maximum utilization of nuclear energy, such as restart of existing power plants and development of innovative light water reactors, of course, with the precondition that safety must be thoroughly ensured, as well as to accelerate the development of future nuclear fusion. Nuclear fusion does not entail the risk of depletion of fuel resources, and the operation can be easily suspended by stopping the fuel supply. It also offers an advantage of not generating highly radioactive waste. Realization of nuclear fusion power generation will solve Japan's energy problems and will greatly contribute to the global battle against the climate change. ITER, an international project on nuclear fusion, has been reached its 80% completion in construction thanks to the effort of everyone related. I strongly hope the operation will start at full scale in 2035, overcoming various challenges. The BA activities progressed by both Japan and Europe are making progress in establishing the technological foundation necessary for nuclear fusion demonstration reactors. Last October, JT60SA, an experimental reactor of Japan, succeeded in generating the first plasma, which is a significant step forward to realize nuclear fusion power generation. And the related facilities or BA activity bases, such as Rokkasho Fusion Institute and Maka Fusion Institute, are also institutions to develop young talent and researchers from all over the world. I believe it is extremely critical for the government to provide further support so that we can build an environment where younger generation can be engaged in the work with hopes and dreams. In addition, there have been startups founded derived from the R&D of nuclear fusion in the fields such as lithium collection and low-temperature refinement of ores. I have high expectations from the development of industries derived from nuclear fusion in Japan. Looking at things around the world, in parallel to ITER, each country is accelerating its own large-scale initiatives. We are entering the age of international competition in nuclear fusion power generation. Under such circumstances, Japan set the Fusion Energy Innovation Technology Strategy, the first national strategy on this subject, in April 2023. It is reassuring to see how the strategy incorporates a promotional structure, establishment of innovation hubs, and industrial councils from the perspective of industry and talent development, in addition to technology development to enable demonstration reactors. I highly expect that the Japanese companies and industries can take the lead in nuclear fusion development, utilizing accumulated insights without delay from other countries. Under the strong leadership of Director General Barabaski, who took the position last September, I hope Japan ITER organization will be more closely cooperating with each other to further promote projects to realize demonstration of the technology. I'd like to conclude my remarks by hoping that the symposium will be a great milestone for further evolution of the R&D of nuclear fusion. Thank you very much. Mr. Izumi-sama, thank you very much.
Next, Mr. Shinichiro Kengaku, the chairperson of the Energy Committee Japan Association of Corporate Executives and President CEO for Sparks Innovation for Future. Mr. Kengaku, please take the stage. Good afternoon, ladies and gentlemen. I am Mr. Kengaku, Chairperson of Energy Committee of Keizaido Yukai, or Japan Association of Corporate Executives. It is a great honor for me to be invited to the ITER BA Annual Symposium 2023 and to address you today. And as a Keizaido Yukai, again, we would like to offer the deepest condolences to our deeply affected by the earthquake in Noto Peninsula. And last month, the Japan Association of Corporate Executive, aka Keizaido Yukai, published an opinion piece entitled Active Nuclear Energy, proposing the ideal nuclear energy utilizing for our future, in which we revised in our position on nuclear energy. The phrase active nuclear energy, which uses a Chinese character utilize meaning in order to make primary energy as fossil-free as possible, it is desirable to utilize nuclear energy with the highest level of safety in the world until the next viable option becomes available. And this is the purpose of the phrase. And as the next viable option, the one we are most looking forward to is the fusion energy of nuclear fusion, which is today's theme. And most of you attending today are probably involved in the fusion energy industry. But most of the people who are not involved in the fusion energy, including as business people, have been aware that fusion is a dream technology for the distant future. However, the global energy crisis triggered by Russia's invasion of Ukraine and the international trend toward carbon neutrality by 2050, which will not stop even in the difficult situation, are forcing each of us to think about energy issues as if they are our own. And the number of opportunities for each of us to think about energy issue is our problem. It's increasing each year by year. In this context, I have noticed a visible increase in the number of opportunities for nuclear fusion to be covered by mass media, such as TV and newspaper, as a safe, carbon-free, and stable energy option since the beginning of this year. And overseas and ICT executives are actively involved in nuclear fusion. And for example, OpenAI founder Mr. Sam Altman has invested in a nuclear fusion startup, claiming that the key to realizing a bright future is a wealth of knowledge and energy. The public's and the world attention and expectation for nuclear fusion may be higher now than ever before. The business community is looking forward to establish the fusion technology as soon as possible, and its inclusion in our country's energy portfolio. We also hope that its presence will increase in carbon neutrality society after 2050. The Keizaido Yukai had the pleasure of visiting the ITER construction site in France 4 years ago, 2019. And I'm sure that you will be able to tell us about more about it today. But I have heard that the site has been making steady progress toward completion since then, with the delivery of all 19 toroidal field coil being completed last month. In Japan, JT60SA has started its operation and has achieved remarkable results, such as a successful plasma production. By integrating these various efforts into the development of the demo reactor, we expect that Japan will be able to complete a competitive fusion plant. The birth of two startup companies from QST is also very important. The new technology that emerges from the cutting-edge field of nuclear fusion can be applied to other industrial fields as well as the fusion. The business community would like to encourage collaboration and cooperation in order to play a role in the creation of such new value. I would like to conclude my remarks by wishing that today's debriefing session or symposium will advance the collaboration between fusion research and development and industry, and that it will be further developed as a platform for the realization of fusion energy by bringing together various participants. Thank you very much for your attention. Mr. Kengaku, thank you very much.
ただいまご挨
In addition to those who have just greeted you, many other guests are in attendance. I would like to introduce some of them here. I'll be introducing from the audience's left to right. Ms. Sachiko Horiba, Member of the House of Representatives. Thank you very much. Mr. Yuichiro Wada, Member of the House of Representatives. Thank you very much. Mr. Toru Azuma, Member of the House of Councillors. Thank you very much. Mr. Seki Soramoto, Member of the House of Representatives. Thank you very much. Mr. Akinori Eto, Member of the House of Representatives. Thank you very much. Mr. Masaki Akaike, Member of the House of Councillors. Thank you very much. Mr. Shinji Morimoto, Member of the House of Councillors. Thank you very much. Mr. Shuji Kira, Member of the House of Representatives. Thank you very much. Mr. Taisuke Ono, Member of the House of Representatives, and his secretary is present here today. Thank you very much. And Mr. Hikaru Masaki, Mayor of Naka City, Ibaraki Prefecture. Thank you very much. Mr. Mamoru Toda, Village Mayor of Lokasho Village, Aomori Prefecture. Thank you very much. We have also received many congratulatory telegrams for today's symposium. Due to time constraints, I would like to introduce only names of some of them. Mr. Yamato Aoyama, Member of the House of Representatives. Mr. Yasufumi Tanahashi, Member of the House of Representatives. Ms. Kuniko Inoguchi, Member of the House of Councillors. Ms. Asako Omi, Member of the House of Representatives. We thank you very much for the kind messages we received.
それでは
Let us move to the keynote lecture. First, we'd like to receive the explanation report on the ITER construction status. First, we'd like to invite Mr. Pietro Barabaschi, Director General, ITER Organization, and then we'd like to invite Mr. Kamada Yutaka, Deputy Director General, the ITER Organization. Mr. Barabaschi, Mr. Kamada, the floor is yours.
Thank you very much. It is I'm here with Deputy Director General Kamada and Chief Strategist Omai-san. It is a great pleasure for the three of us to be able to attend to this meeting. Unfortunately, remotely, we would have liked all of us to be there with you, but time constraints and of course our job here in ITER could not allow that. Let me start by expressing our condolences to all the victims of the Noto Peninsula earthquake. And let me move on to my presentation now, where I introduce the status of the ITER project. Yes, thank you. So next slide, please. So you will see here an overview, literally a bird's eye view of the ITER site as it is today. We have very great progress on most plant support systems, which are operational and under commissioning, and 80% of the civil works have been completed. So great progress. Please, next slide. On-site progress in construction and installation is visible in a number of photos that we present to you here. In the upper left, you will see a picture of the reactive power compensation, which is to the largest extent, fully installed. We have that the magnet power conversion equipment, the power converters driving the magnet are also fundamentally installed. We have on the lower right, the cryogenic system, which is completed in its installation and pre-commissioning is underway. And you see in the upper right a view on the cooling water system, ready to exhaust all the heating power that will be produced in ITER. That is also fully installed and commissioned. Next slide, please. We have the control system building, which is ready for equipment. We have that, I said before, 80% of the civil infrastructure is ready. We have still some work to do, and you see the final concrete pour on the tritium building being executed as we speak. And we have the central solenoid modules coming from the United States are now step by step coming, two of which have been already aligned and stacked. And as I will show you, a fourth module is now arriving on the site. The largest building, the PF coil fabrication building, is now being repurposed for repair of components and for the purpose of port plug testing. Next slide, please. Next slide, please. Here you see a view in the assembly hall. This is where the components for it are being assembled before they are lowered in the pit. You will see later also in a movie a view flying through this assembly hall. And you see here the two-sector module assembly tools where the modules are being assembled. And this is in a phase in September 2023, as I will explain you, where we were disassembling some of the sector modules in order to perform later some repair work. Next slide, please. Indeed, we found, as we joined, myself and Dr. Kamada, that we had to do some repair work in some of first-of-a-kind components. These things happen. We had experience ourselves of such things happening in other machines, and we are not discouraged. We will repair this work. We had some non-geometric, geometric non-conformities in the field joints of the vacuum vessel due to weld distortions. These are being repaired. Next slide, please. And we also found that we had some signs of defects in some of the cooling pipes of the thermal shield, which prevents the heat flux to be radiated from the vacuum vessel to the magnet. So these cooling pipes need to work and perfectly, and we found some indication of stress corrosions, and we decided to proceed with the repair work. So repair work is now ongoing on these components. Next slide, please. So repairs, as I said, are underway. We have the vacuum vessel sector 6, number 6 has been removed from the tokamak pit. Both 6 and 7 have been completely disassembled, and the thermal shield piping has been removed, and repairs and replacement, as I said, are underway in the PF coil building. Next slide, please. Manufacturing is continuing on the various components that still will need to be assembled. You see a view in the upper left of the cryostat lid, which has been completed by India and in storage. And in the upper right, you see the last toroidal field coil from Japan, which has arrived on site. This is a very important news for all of us. When I started working in the ITER project, I thought that this would have been the most complicated project to complete, the TF coils, I mean. And it is very, very pleasant to know that all TF coils, which is the backbone of the ITER project, are now on site. So we have the last from Japan and also the last from Europe that you see in the right side of this slide. We have now more in cryostat feeder components, which have been also delivered from China, and all of these are now being assembled. Next slide, please. As I said before, we had 2 central solid modules being stacked. We have a fourth one, which has been delivered from the United States. There will be more to come soon. We had the last AC/DC converter unit, which has been delivered from Korea, and it will be assembled shortly. We have 8 cold valve boxes, which have been delivered by Europe and have been, integrated in the cryoplant system for further commissioning. And we have the last of the poloidal field coils, which was delivered last year from Russia. So the entirety of the toroidal field and the poloidal field magnet system they are on site and ready to be assembled. We miss still a few of the central solenoid modules, which will come last, also because they can be assembled separately on a later phase. Next slide, please. We have also decided with Kamada-san that we could take some of the time in order to do some additional testing on the TF coil systems. As I said, these are the backbone of ITER, and we wanted to mitigate some of the potential risks, and therefore we have decided to create and build a toroidal field coil test facility here on site. In this facility, we will be able to test some of the toroidal field coils and also the poloidal field coil number 1. It is sized and large enough in order to do that. So a complete unit energization up to full current together with a fast discharge unit will be, connected to the TS facility, and the existing cryogenic system will be utilized. I remind that all coils that have been assembled in JT60SA that started operation, as you know, and as it was said recently, we are tested. We will not be able to test all the TF coils of ITER, but we will be able to test a number of them. Next slide, please. In the rebaselining effort, we have also decided to change the first wall material of ITER from beryllium to tungsten. And why did we do that? We did so because we think and we know that the beryllium is not a material which can be utilized in demo because of excessive erosion. It will not be able to sustain the duration of pulses that will have to be endured by the demo reactor. And so we wanted therefore, to utilize ITER to anticipate this research and development to ITER and to ask the fusion community across the world to be able to make sure that the tungsten would work in ITER, and of course, as it will have to also in the demo reactor. So that has been also a key of the changes in the project that myself, together with Dr. Kamada, we have impacted. You see here one of the first wall modules that will be installed in ITER. They are shaped like a bird in order to smoothen the heat flux coming from the plasma. Yes, please, next slide. We have also reformulated in the baseline the deuterium-tritium operation in 2 distinct phases. The objective of these phases, DT1 and DT2, will be different. The first phase will focus on the achievement of a burning plasma, so the so-called Q equal 10 objective of ITER, whereas the second phase will focus in achieving the fluence that will be, planned for the ITER project. So that also is a way to facilitate the explanation to the nuclear safety body here in France, and has been broadly welcomed by the nuclear safety body in the frame of our safety demonstration. So the so-called DT1 and DT2 will be the basis of the operation baseline in the work that we are doing together with Kamada-san. Next slide, please. So I just spoke about preparation of a baseline. This is our task now. It is under the responsibility of Dr. Kamada. The preparation of a new baseline for submission to the ITER Council in the middle of 2024 is now the focus of our attention. The baseline that was prepared last time was in 2016. There is a major review underway, and as I said, we will present this in the middle of 2024 to our stakeholder, the 7 members represented in the ITER Council. So what is the overarching objective of this new baseline? Has been to reprogram the activities in order to maintain and the achievement of Q equal 10 at the earliest possible phase, to include in our baseline a realistic plan to mitigate risks whenever this would be possible. there are a number of considerations that had to be taken into account for the preparation of the baseline. We had delays from COVID-19 that significantly impacted our work here, and first-of-a-kind technical challenges that I have introduced to you. We had to work out on realigning our cooperation with the French nuclear safety regulator, and I'm very pleased to say that after 1.5 years of working together with Kamada-san, we have now a very, very good relationship with the regulator, which allow us now to engage in a more constructive way, explaining them all the features of ITER. We are reconsidering the sequencing of the vacuum vessel welding in order to mitigate the risks during welding, in order to mitigate the effect of weld distortions. We should never forget that it's the first time that we assembled such a big tokamak. So we have a lot of experience that came from the JT60SA, of course, tokamak in Naka, but ITER is bigger, and we should not underestimate the problem of weld distortions. And for these reasons, we are reconsidering the sequencing in order to mitigate this effect. As I said before, we will proceed with the testing at cryogenic temperature and full currents of some of the toroidal field coils. And we will prepare a first plasma campaign to mitigate or risk, followed by the 2 deuterium tritium operation phases. So these are basically the pillars around which we will prepare the new baseline to be prepared and submitted to the ITER Council, yes, in the middle of this year. Next slide. So lastly, I would like to thank you. And here it's a photo with where the ITER project had the great privilege and honor last November to meet the Japanese Prime Minister Kishida. You see this photo with, of course, with my 2 close collaborators, Kamada-san and Omae-san, and also with the member of the House of Representatives, Taira-san, who I really would like to thank, like all of you, for the great support that you have for the ITER project. We are doing our best to recover a slightly difficult situation in ITER. We have full of, say, trust that we will recover successfully the technical difficulties that we are having. And now I would like to leave, yes, the floor to Kamada-san that will be able to show you a movie around the ITER site. Thank you very much.
Okay, so please start the video. Thank you very much. I'm Yutaro Kamada, ITER organization. そう、ありがとうございます。ご紹介いただきました鎌田です。これからITERの建設現場をご案内します。ここはアセンブリホールです。まず日本の超電導トロイダル磁場コイルですね。高さ16メートル、重さ360トン。左側もコイルです。で、この真ん中にありますのがプラズマを入れるドーナツ状の真空容器の一部、40度セクターです。440トン。で、これらを組み合わせていきます。で、今見えている
And we are putting those together. And in the middle is that we have solenoid, and the solenoid made in America. And there are 6 coils, and we put all those coils together, and it 20 meters in total, and we made it halfway through. We are almost halfway through. This is the ITER site. This is the overview of the ITER site. And this is the power plant. And we have all completed steady-state electrical network. This is the cryo plant. And this is to cooling coil to cool, this is a cooling plant to cool down heliums. And so for superconducting magnet by absolute, we have to keep it at the certain temperature, and we use this process line. This is the circular pipe distribution gaseous liquid helium, and once the liquid helium is sent from the plant, it's delivered to the tokamak facilities. And this is the tokamak facility, and this is the SAT. This is the this is where we remove heat. This is the cooling tower, and all the heat generated, 1.2 gigawatt heat can be removed. So this is the overall of the facility. And now this is the colloidal field coil assembly construction site, and we have 6, and out of 4 there are too large to transport. So we built them. We needed to build them in on the site, and that largest one is like 24 meters in diameter, and we are almost completing all the coil construction. And at this site, carrying plasma, we are going to install all the facilities and equipment, and we're going to test coils. And this is the radio frequency building, and so it's like a 2,000 times more than household radio frequency. We have 24 units of them, and 8 of them are transported from Japan. And this is the tokamak control room, and we have completed the construction of the building. And here we are going to operate ITER, and using control equipment and devices will be installed, and engineers and researchers will gather together to run these facilities. And JT60SA, who have experienced that equipment, I expect them to show their leadership. And this is the neutronium beam building, and we have building the frameworks, and now it started take shape, and we will have 1 million volt made in Japan, and to heat beams we need to inject 1 million volt into the beam. And so back to the construction, we have tokamak pit underneath this building, and we can see that. And this is the 2022 that we installed the very first module, and that's the one on the top. But there were some problems, and we were not able to combine with the next module. So back in June last year, and we had to do it again. We have to remove it from the outside of the tokamak, and now we are doing the repair work. And the vacuum vessel is so massive and huge and complex, and this is something no one has experienced before. And it was unfortunate that we had some problems, but we are willing to overcome all the problems to make sure that we can put these facilities together so we can contribute to nuclear fusion energy production. Thank you very much. That's the end of my presentation about the construction site. Dr. Balabaski and Dr. Kamada, thank you very much.
Next speaker is Mr. Daisuke Baba, Director, International Nuclear and Fusion Energy Affairs Division, Research and Development Bureau, Ministry of Education, Culture, Sports, Science and Technology. He'll be giving a lecture on fusion energy innovation strategy. Mr. Baba, please. Thank you very much for the introduction. I am Daisuke Baba. I'm in charge of fusion energy at the MEX and also the Cabinet Office. Today, I would like to talk about the government's support as a national strategy in April. This was established as the National Strategy Fusion Energy Innovation Strategy, and I would like to talk about this national strategy today. For the first half of this presentation, I'll be talking about the overview of this national strategy. Another half of this presentation, I would like to talk about some recent activities that many of you have already talked about, JT60SA's achievement from how the point of view of governments, how the government is looking at these activities. And this fusion energy innovations strategy, the main point is the credit on the left. So far, ITER, including ITER MBA annual symposium, when it comes to fusion and ITER, the Ministry of Education has been promoting and taking the lead. However, as the government as a whole, we recognize the importance of fusion energy. So the government as a whole, including the cabinet office, are now involved, and that is our intent for establishing this national strategy. Another point is that we are recognizing this as an important industry, and also DTP are the three important pillars: deuterium, tritium, and plasma heating, and these are the sort of sync to these alphabets. And I would like to talk about these points as well. So the condition, the assumption is like this. As already we heard, what's behind why we are recognizing this as an important industry is as we are regarding this as a promising solution for the society, and also for environmental energy solution. And so the future energy as a new industry, as you can see here, the investment trend is shown on the graph. Yellow sees the DOE Energy Department of the U.S. Investment, and the blue shows the private investment. So you can see that private investment is also increasing. And as we already heard, Bill Gates, Amazon, Jeff Bezos, a lot of people, Altman, CEO of ChatGPT, a lot of those private CEOs are making a lot of investment. What's behind this is increasing data centers and generative AI. Huge amount of powers is needed, and so this is leading to the investment in fusion energy. Of course, as Japan, including KST, a lot of organizations and the government and industries are now recognizing this importance and establish this national strategy. So these are the three pillars. D, first, developing the fusion industry. In this pillar, the important point is visualization. The government is trying to accelerate the research and development to realize demo. And the second pillar is connection. For this D, this year, we are trying to establish Fusion Industry Council of Japan. Already overseas, the US, UK, and Germany, we are now, they already have the industry councils, and Japan also would like to have this council because we have a lot of related industries in this fusion energy. Also, a standardization of regulations for safety, like UK, Canada, and other countries would like to also cooperate with these countries. And then the second pillar is technology, T. And regarding this, the overall trend is the miniaturization and sophistication as a game changer for future fusion energy, and also we're using the ITER project and BA activities. We are trying to acquire the core technologies, and also we will be promoting the research and development for the future further. And the third pillar, P, promotion. Regarding this, the Cabinet Office is leading tower for the government, not only the MEX, but also the Ministry of Economy and other governmental ministries and agencies will be cooperating together to promote fusion energy. That is the big shift in our country. And also for the development of demo. Look, we heard from Lokasho Village Mayor, but we will be pulling together academia and private sectors, including QST, and for promotion. And also, we have a lot of students here in the attendance. We will be clarifying the career path for this fusion energy, so that we can nurture the talent. And now I'd like to talk about recent activities based on this strategy. First of all, this is our overall research and development picture. ITER project and JT6SA, and also we we have a laser laboratory from Osaka University, and also the NIFS, National Institute for Fusion Science, are actively engaged, and we are also supporting startups. So we established Small Business Innovation Research Fund, and also we are discussing using our other policy activities for promotion. And JT6SA, I would like to briefly touch upon this. Last year in October, 10 years after starting assembly, we for the first time achieved plasma. On December 1st, JT60SA inauguration ceremony was held in collaboration with Japan and Europe in Naka Institute. And also a lot of people from Europe participated in this ceremony. And thank you very much. This JT60SA is in Naka Institute, and this is established in collaboration with Europe and Japan and operated in collaboration between them. And as Dr. Balbaski said, at this timing of the inauguration ceremony, Mr. Balbaski and Mr. Kamata actually had paid a courtesy call to Prime Minister Kishida. And Prime Minister Kishida appreciated the collaboration between Europe and Japan and congratulated us for this plasma generation. And also he set the fusion energy national strategies and further promotion to promote the industrialization of future energy. And then regarding ITER Council, I also attended this 33rd ITER Council. What's notable was first plasma achievement. That was not only from Europe, other countries were also interested in hearing more about this. And they are saying that all the communities, not only from Japan and Europe, should say, commemorate and send congratulatory messages in communication. And also, this was what Moriyama said.
As next, we'd like to utilize the collaboration internationally. I'd like to utilize the moonshot R&D system so that we can enable the support for emerging technologies like downsizing and sophistication of technology. And the Samsung EU Commissioner for Energy joined the meeting as well. The 32nd BE Steering Committee was held, and the joint press statement was made here in the Council. In Japan and European countries decided to strongly promote the activity in BA. And also, as the steering committee, European research will be supported and expressed gratitude for Rokkasho Fusion Institute and related institutes. And also, December 1st, Minister Takaichi, as mentioned in the beginning, mentioned the industry forum will be set up by the end of this fiscal year, as well as safety regulation will be further considered in her remark. And this is the overview of the Fusion Industry Forum. Perhaps some of you are already aware of this based on the information. And also, 19 initial companies registered for the forum. The name was disclosed on the website related to this Future Energy Forum. This is a tentative name, but this is the name for Nuclear Fusion Energy Forum. Now, what is surprising in a good manner is that not ITER suppliers, but also companies in the fusion-related startups, or energy-related companies, and trading houses and communication companies are have made an application for this. So many companies got together to join the forum, and as the government, we'd like to closely cooperate with the Fusion Industry Forum, and would like to further increase the member of the forum. And by the end of this fiscal year, we'd like to officially kick off this forum. On a different topic, as the country would like to touch on an example to utilize global collaboration. COP28 held last month, December last year, in the United States mentioned that they'd like to closely communicate with the international communities as strategy to realize fusion energy, a supply chain establishment, regulatory framework, and talent reinforcement and understanding and improvement are not something Japan alone can solve. We'd like to closely communicate with other countries, including the US. So we'd like to promote this initiative and cooperating with other countries. And in line with that, the comprehensive economic measures, and this was released last year. ITER BA would be at the core of these initiatives, but also Moonshot R&D program. Utilizing this program, we'd like to add the program related to fusion energy and headed by Prime Minister, and this is a meeting and led by him. And this is difficult to see in small letters, but the Moonshot R&D is based on the concept of President Kennedy's Moonshot initiative. So in Japan, we'd like to create a challenging promotional program to support R&D as the government. And we've set 9 objectives for the program: artificial intelligence, quantum, environment, medical, and also as additional and another objective, we added fusion energy for this item to be covered by the program. And the next, we would like to set up a initiative and concept for this, and like to start an announcement for the application for the program so that we can facilitate participation from various sectors. The slide shows what CSTI decided on recently. By 2050, we'd like to utilize fusion energy in multifaceted ways so that we can be in harmony with the Earth, the environment, as well as creating a society with invigoration, free from resource constraints. In the future, we'd like to use a baseload power source and utilize the nuclear fusion for that purpose. But for that to be achieved, we need to consider a small power source and off-grid and various applications. And by doing so, we'd like to set various milestones for this energy. And the main implication from this is that ITER, BA, and DIMO reactors, and these are, of course, the milestones, but the path to achieve these would be very long and challenging, needless to say. And ITER, as you're aware, ITER means the road, a path, or journey in Latin. And R&D, going beyond the generations, require support from many people, as well as attract so much excellent talent. And in doing so, the Moonshot R&D program will enable, for example, us to realize a small-scale power source or off-grid power generation or various applications. By doing so, we would like to attract so much excellent talent to find this field more attractive. And by doing so, we'd like to attract so many people from various industries to enable base load power utilization of nuclear fusion. So that is the path we'd like to create through these initiatives. Lastly, this is the takeaway. We'd like to set up the foundation to enable nuclear fusion demo reactor, and would like to accelerate R&D and reinforce the talent development. For that to be achieved, we'd like to officially set up and kick off industry forum, including invigorated private companies, including startups. As of the year end, we've seen so many companies gathering for this initiative. I think that is something, and we can leverage our capability and skills in this field. And also, we'd like to promote international activities strategically. Today, we have so many members from various embassies of various countries, and this is something we are to give it a challenge as the humanity, and that for that to be achieved, international cooperation would be a must. We'd like to further strengthen our activities in multilateral and bilateral relationship for ITER and BA included as well, and the Moonshot R&D program, as well as promotion of various research and study. Through that, we'd like to let so many people to make a bet on nuclear fusion and ITER and BAs. And lastly, this is a photo. When I visited the ITER for the first time, I think this was the symbolic photo. In the center He is an internship coming to the ITER and postgraduate, and Kamata-san and the professor from University of Tokyo are here in one photo. So this is very symbolic picture I wanted to show you today. Fusion energy, of course, as Director General Balbasky mentioned, this is not something we can achieve easily. Going beyond various generations, we need to be cooperate with various countries and spending so much effort and time and effort. The government and MEX would like to strive to realize this, and not just the industry forum, but also universities across the country and students. We all would like to cooperate with each other so that we can make this happen as soon as possible. That concludes my explanation. Thank you all very much for your kind attention. Mr. Papa, thank you very much for your presentation.
続き
Next, Mr. Satoru Higashijima, Deputy Director of Naka Fusion Institute at QST, and he is going to present us titled Progress of ITER Project and Present Status of JT60SA Integrated Commissioning. Mr. Higashijima, please take the stage. Thank you for the introduction, and I am from Naka Institute. Naka Fusion Institute. I am Higashijima, and upon the commencement of presentation, again, I would like to deeply offer my condolences to those who are deeply affected by the earthquake in Noto. And as soon as possible, I hope that their life come back to or normal as soon as possible. With that, I like to start my presentation. It's titled It's a progress of ITER project and present status of JT60SA integrated commissioning. I like to share some of the achievement at our institute. And first of all, as Mr. Baba mentioned, April last year, Chief of Cabinet compiled Fusion Energy Innovation Strategy. And since then, nuclear fusion energy has been referred as fusion energy. And that Japan's roadmap toward the realization of fusion energy is what I like to briefly explain using this slide. Currently, through international cooperation, we are implementing ITER project as an experimental reactor. And we have a broader approach activity, which is JT60SA, satellite tokamak business, and at Rokkasho, IFMIF and EVEDA project are underway. And prior to this, at JT60SA, the scientific feasibility of fusion energy was confirmed in the test equipment. And with that, the experiment, we are at the stage of testing demo reactor. And here, our Naka Institute, this shows the yellow part is what we are responsible for. Naka Institute. And Naka Institute is promoting ITER project and JT60SA project in integrated manner to build the technical and human resource base for demo reactor. So first, about ITER project. That we procure equipment necessary for ITER, so that's what we do. And as Mr. Balbasky and Mr. Kamata presented, between ITER and us to facilitate execution of the project as a domestic institute, we facilitate or communication amongst the stakeholders or participants. And JT60SA, and we also share resources and share knowledge and nurture development knowledge. So that's how we contribute to ITER. And at the same time, in high voltage plasma, that's something ITER cannot do, is that's where we come in to contribute to demo reactor. And in BA activity, Europe is our counterpart. And also in BA activities, some institutes are showing interest. And the US is showing strong interest in the BA activities. And we coordinate communication amongst those stakeholders. And more than ever, it's getting a lot of attention in this field. Businesses or a business community and industry, it's really important to bring them on board. And as I mentioned earlier, as is stated in the Fusion Energy Innovation Strategy, development of a demo reactor, we need help from academia and private sector to develop technology. And we set up a fusion. We set up a Fusion Technology Innovation Center. So I like to explain what ITER project is. And as Mr. Kamada presented, this is already what was presented by Mr. Kamada. This is the drone video of ITER, and as we walk you through, I will show you this video. I like to explain. So the ITER project is managed under the leadership of ITER organization with international cooperation of Japan, Europe, Russia, the United States, China, and Korea, and India. So the significance of ITER is to obtain the prospect of realizing fusion energy, and technical goal is to actually use deuterium and tritium as fuel. And it is to achieve the ratio of fusion output, the value of more than 10, and the plasma burned is to be maintained more than 400 seconds. And then combine those superconducting technology and verify the technology, and also blanket and other equipment should be tested to make sure that it's safe for environment and for people. So that's the purpose of ITER. And main parameters, and tokamak size is 30 meters in diameter and 30 meters in height. And output is 500,000 kilowatt. And using deuterium and tritium by 2035, we would like to be able to be operational. And to that end, we are putting equipment and facilities together. And this graph, ITER project itself is, we are in the phase where we are acquiring equipment and putting equipment together. And here you can see ITER on this page explains the equipment or instrument that we are procuring. And this requires high technology and superconducting toroidal field and solenoid, CS, diverter, and remote maintenance equipment, measurement equipment, neutral beam, injection heating equipment, RF heating equipment, and tritium plant equipment. So as you can see in the white, so those are the roles and responsibility shared amongst the parties to acquire those parts. And a toroidal TF coil, and a solenoid and CL coil conductors. We have already completed acquiring those parts and bits. And QST and JADA, Japanese institutes organization, and following the baseline. We follow the baseline in acquiring those parts, and our mission is to procure those parts and deliver without delay. So we have only a limited amount of time. So I like to focus on the TF coils and the CS coils, which was a significant achievement last year. And first, TF superconducting toroidal field. Superconducting toroidal field. And we were responsible to acquire 9, and 1 is for spare. And TF coil, it's 16.5 meter in height and 9 meters in width. And it has consists of winding section and superconducting conductors in a structure. So TF coil, production with TF coil, Mitsubishi Heavy Industries, Mitsubishi Electric Corporation, and Toshiba Energy System help us to achieve that. And the spare, which is one unit, is a spare. In November last year, was delivered to ITER construction site. And since 2008, we signed the contract. It took us 15 years to put that together, and all the makers and Japanese companies who help us to achieve this in the past 15 years in procuring those equipment and parts, and also putting 9 units together. With the help of those companies, we were achieved that. And this is the picture that we are delivering last TF coil, and ITER we completed. So for celebrate our achievement, we received ITER Award 2023 together with European players. Next, diverter. Diverter, the bottom part, the outside target, outer target was our responsibility, and the size is that a diverter is 1.3 meter in length, and a tungsten. It's made mainly of tungsten and plasma facing unit, and it has a backbone tungsten modules, monoblocks, and plasma facing unit PFU prototype. ITER we passed the ITER certification test, high heat and load test, and we started testing PFU, and monoblocks and support structure, the target prototype, outer target prototype. And today, we are testing helium. We are in the last phase of testing high temperature helium leak test. And outer target prototype, again, Mitsubishi Heavy Industries, Osaka Yakin, Kinkin, Giken, LMA, Applied Material, Daiwa Alloy, and Daido Steel cooperated to a great extent, and also high temperature helium leak as Kegawa Electric Industry was played an indispensable role. And next, JT60SA. Next is the JT60SA. And so I'd like to show you a video, drone video, as I explained. As I mentioned earlier, and Japan and Europe work together through the VA activities. But also we have our own plan, JT60SA. This is a Japan's own plan. So main parameters are tokamak itself is 13.5 meters in diameter and 16 meters in height. And it accounts for almost half the size of ITER. And I often explain when we give a tour on the site, I often tell them that so it's almost as high as the Nara's giant Buddha. And the plasma current is 5.5 mega ampere, and toroidal field is 2.25 T. And also diameter and radius, there are important parameters. And the plasma flat top is 100 seconds. And the heating time or heating and current drive power is 41 megawatt. And for JT60SA, we are also testing confinement. And we do not use deuterium or tritium in testing. And JT60SA is the only large tokamak equipment and device, and I think we have the capability to provide large support to ITER, and we mainly focus on steady-state high-pressure plasma research, which is not difficult at ITER. And next, roles of JT60SA. I'd like to briefly explain JTXT. To achieve demo reactor, there are a few things that we need to overcome. Is to improve economics of the this action. We need to make ITER equipment smaller, which must be achieved. With high plasma, we need to be able to produce high plasma pressure. That is because the fusion energy output, plasma pressure works in a square, and if we improve plasma pressure, that improves efficiency. And I like to analyze or liken ITER JT60SA to a bicycle, and the ITER is a rear wheel using fusion. This is to apply fusion energy. It provides but the JT60SA using that the only large tokamak device. So this is a rider. So this is we play as a rider to develop next generation leaders, and as a front wheel, we identify issues ahead of ITER so that we can spearhead ITER project. And higher than ITER pressure, we operate at a higher pressure and make device smaller and more advanced. This is to set the speed of the development speed. So it's a gear. That's what we play as well. And as a tokamak, ITER and JT60SA, we need both of them to be able to apply fusion energy.
Next, I'd like to talk about this achievement. Last year, we made significant progress in integrated test operations. First, let me explain about the integrated test, the purpose of this test. But before that, assembly was started in 2013, and we were able to assemble a vacuum vessel and use superconducting coil with great precision, with an installation accuracy of less than 1 millimeter. After we completed the assembling process in March 2020, we started integrated test operations. The integrated test proceeds like this. 1, evacuation of the vacuum vessel and cryostat to coil cooling. 3, confirmation of transition to the superconducting state. 4, coils energization test. And 5, plasma operation. So we proceeded with the integration test at each equipment and facility and started with number 1 in September 2020. And then we successfully completed up to number 3, this confirmation of transition to the superconducting state. So we conducted this superconducting test. But then in March 2021, during this process, a short circuit event occurred at the connection of the EF1 coil. So we had to put off the integrated test. As we did our research, we found that there was an issue with the insulation structure. So we had to repair it. We completed the repair of about 100 similarly structured conduits, which had been developed for about 2 years. Also, in order to protect superconducting coils more, we made modifications to reduce unwanted voltage, such as ripple, to be applied to the CS or EF coils in a similar event. As a result, we were able to secure the performance required for the first plasma and resumed the integrated test operation in May of last year. Now, I would like to talk about the highlight of the operation, the plasma. The integrated test operation went smoothly, and we completed the energization test of superconducting coils on October 19th. The next day, Friday, October 20th, we started generating plasma. At around 5:30 p.m. on Monday, October 23rd, the second day after the start, I would like you to play the video again. So in this way, we succeeded. The plasma is very short, but in just 2 days, we are able to succeed in generating the first plasma. This was the result of preliminary studies using a newly developed plasma simulator. The plasma parameters are described here. the plasma current was 130 kiloamperes or 130,000 amperes. Please play that again. And this is the discharge duration, about 0.5 seconds. You see round plasma. This was our first plasma. Gas used was helium, and the temperature was 0.3 electron volts, about 3 million degrees. So the significance of the achievement of the first plasma is that each piece of equipment and facility which was constructed and delivered under the international cooperation functioned together as a system. And as of today, this is the world's largest superconducting tokamak device. I was able to build this and operate this. So I believe that this achievement will provide a firm prospect for ITER, which will be constructed in a similar manner. I am confident. By the way, by the achievement of plasma, this great news from Naga City, the local area, we were awarded with special awards for this achievement. And integrated test operations using plasma, this itself proceeded smoothly after plasma achievement. Mega ampere class diverter, mega ampere is 1 million ampere class diverter plasma. This was achieved. On the left, you see this video for 10 seconds was the plasma discharge time, and the plasma current was 1 mega amperes, and it was on November 27th. And in a similar way, EC power extended smoothly, and on the same day, we increased the plasma current to 1.2 mega amperes or 1.2 million amperes. We are able to use these plasma parameters to have the diverter plasma ampere. This mega ampere diverter plasma achievement of this is that we are able to demonstrate control of the position and shape of the plasma according to command values in a tokamak device with superconducting coils. And this will enable us to control larger plasmas in ITER and demo. Next. While the integrated test operation was going on smoothly, we also held a ceremony to commemorate the start of JT60SA operation on December 1st last year. At the ceremony, with the presence of Minister of Education Mr. Moriyama, Minister of Science and Technology Ms. Takaichi, and European Commissioner Ms. Simpson, we did a plasma demonstration, and so we actually asked them to press the button for discharge sequence, and as a result, as you can see, we were able to have the 1 mega ampere diverter plasma. You see a beautiful diverter plasma behind the ministers and commissioner. And during this ceremony, Minister Moriyama and Commissioner Simpson had a meeting and signed a joint press statement on future energy, expressing their support for the advancement of JT60SA and their intention to strengthen efforts for future human resource development. Also, as you can see here, at the same ceremony, the title of world's largest tokamak was handed over from JET to JT60SA. The photo on the right shows Mr. Done, CEO of Eurofusion, presenting the certificate for the world's largest tokamak to Mr. Shirai, the project leader of the satellite tokamak project at the time. Next, I would like to talk about our future plans. The main part of the integrated operation was completed, and we will be enhancing the device. And in December, we completed the main part, and we have started to further enhance the equipment. Specifically, the in-vessel components, heating devices, measurement devices, and other equipment will be improved over a period of about 2 years. After that, full-scale plasma heating experiments will start. So the integrated test has already completed. As you can see, the inside of the vacuum vessel was only equipped with a limiter to protect the wiring and other components and a diverter on the top side. The measurement equipment was also limited like this. And the heating system was constrained to 1.5 megawatts of EC at the injection power. But after the upgrade, you can see here, we have 3 items here and here, stabilization plate, and also we will be using diverter using a cassette structure. As a heating measurement, EC power will be doubled. And also as heating measurement, NBA will be used for the hydrogen 19 and for the deuterium 26.5. And regarding the measurement device, we'll be able to measure the plasma, and also a cryo pump will be introduced. And also the another thing will be also pellet injection device will be equipped. This will enable the JT60SA to fulfill its original potential. So the full-scale plasma heating experiment, the experimental team has started taking actions. 3 leaders were selected, and 6 topical group leaders were appointed. And in this experimental team, they are discussing important experimental items and future research activities after the equipment upgrade to decide priority instruments and actuators based on objectives, to report on the latest research and review the JT60SA presentations. Participation in the experimental team in Japan is being done through QST's call for core plasma collaborations. Next, lastly, I'd like to talk about our human resource development. With the aim of fostering talent who can internationally active in the future of the fusion energy field, JT60SA International Fusion School GIFS was held. The first one happened from September 4th to the 15th, and students were selected from both Japan and Europe. 20 from Japan and Europe, a total of 20 students. In addition, we had from Japan, Europe, and the ITER organization, we had 24 leading researchers. The school consisted of an opening ceremony, classroom lectures, experiments, and a reception, and was well received by both students and lecturers. And JT60 is at the after the inauguration ceremony and joint press statement, we will be also intend to have this further class in a further bolstered manner. Today, I have reported on the recent R&D activities on the NECA Institute. In summary, with regard to procurement of ITER equipment, we completed manufacturing of all superconducting toroidal field coils. And we started procuring other components such as tungsten diverters. Regarding JT60SA project, we repaired superconducting coils installation and reduced unnecessary applied voltage to the coils, among others. Because that secured the performance required for the first plasma, we resumed the integration test. October 23rd, we achieved the first tokamak plasma. November 27th, we succeeded in generating the mega ampere class diverter plasma. December 1st, we had the inauguration ceremony to celebrate the start of JT60SA operation, and we successfully completed the integration test. And using GIFs and others, we will be further promoting our talent, and we will be collaborating with industries through the Fusion Technology Innovation Hubs and among others. Thank you very much for your kind attention. Mr. Higashijima, thank you very much.
Yeah, I'd like to introduce some of the participants. Mr. Susumi Yamaguchi, a member of House of Representatives, and his secretary is with us today. Thank you. Next, we would like to invite Mr. Hayashi Takumi, Deputy Director General, Rokkasho Fusion Institute, QSD, with the title Progress in BE Activities at Rokkasho Fusion Institute and Social Implementation of Fusion Technology toward the demo reactor. Mr. Hayashi, the floor is yours. Thank you for your introduction. My name is Hayashi, Rokkasho Fusion Institute, QST. Thank you very much for giving me this opportunity to talk to you. Thank you very much. And as mentioned by Mr. Higashijima, I'd like to also express my deepest sympathies to the people affected by the Noto Hanto earthquake. And Rokkasho is in an area close to the coast. We'd like to take appropriate countermeasures for the disaster as well. This is the title of my presentation, Progress and BE Activities at Rokkasho Fusion Institute and Social Implementation of Fusion Technology toward Demo Reactor. You have already seen similar drawings, so I'd like to give a brief explanation on this. And this shows the development roadmap to realize demo reactor. At the moment, ITER is under construction, and we'd like to demonstrate that a nuclear fusion combustion, and then we will be moving to demonstrate power generation using the demo reactor. And broader approaches have been already explained via activities. At the Rokkasho Fusion Institute, promotes 2 of these projects out of these 3. The first one is the IVAC business related to design R&D and supercomputer theoretical simulation, as well as ITER remote experiment activities. These are what we promote at Rokkasho Fusion Institute promotes. And also the International Fusion Materials Irradiation Facility, IFMIF, as well as the engineering validation and engineering design activities. We are now promoting the development of the world's highest current accelerator, and IFMIF and IVITA, a project on these. Last year, I gave a very detailed explanation, and the demo accelerator beam testing is underway. And this fiscal year, the development of radio frequency quadruple accelerator, or RFQ, and the testing for this is in progress. Especially, we succeeded in the cooling performance as well as the high stability A-beam transmission as well. In particular, high output radio frequency incidence testing, we are now showing progress to achieve a continued operation at the rated voltage. And ITER project with regard to computational simulation remote experiment, we are collaborating with the ITER organization. This photo shows how we succeeded in the remotely conduct live monitoring of the ITER plant data. In the demo reactor design and R&D, we are seeing progress in the R&D with regard to blanket in particular, including the domestic plants. And blanket-related research is something I'd like to report to you today. But before doing so, I'd like to briefly explain the principles of a nuclear fusion reactor as well as the blanket, what they are. As you are already aware, in nuclear fusion power generation, we use these types of vacuum vessels and creating superconducting coils, creating a basket of lines of magnetic force, and heat deuterium and tritium to let it in a plasma state to cause nuclear fusion, and the energy generated will be carried away by neutrons within the vacuum vessel's blanket. The structure will be provided, and within the blanket, the neutron's kinetic energy will be converted to thermal energy to generate power. And within the blanket, there is another role for the blanket. Within the blanket, there will be functional materials, to be more specific, materials to increase neutrons, such as beryllium. And the increased neutrons will be in reaction with lithium, and that will lead to the self-generation of tritium, one of the fuel of nuclear fusion reactor. That is the role the blanket serves. As mentioned in the opening remarks in today's symposium, this functional material, the R&D, I'd like to talk about the current status as well as the result. They are in progress. That is something I'd like to focus on in my presentation. Let me first talk about the important factor, beryllium, to increase neutrons from the perspective of securing a resource. Beryllium itself is not something very familiar to you, but this material is used as an alloy material with copper. This is very effective for that purpose. However, as a resource, Japan is totally dependent on the import. And to create a demo reactor, you need about 400 tons of beryllium and reactor, and you need to replace that every 4 years. And beryllium ores abound in overseas countries. You can see this is the distribution of beryls. However, when you inhale the powder of beryl, that will cause severe pulmonary inflammation. Thus, it is designated as specified chemical substances. From the beryls, to extract beryllium out of the ores, you need to consume significant amount of energy. That is the problems that we are to suffer with this material. So at the moment, a company in the United States nearly exclusively produce and sell this material, and the production amount is just as small as 300 tons per year. And therefore, to stably secure beryllium and this resource for Japan, we need to develop the refining technology with good economy and safety. This slide shows the general process to extract and refine beryllium from beryllium ores. But beryls have very stable crystal structure and difficult to dissolve. You need to use external heating up to 2000 degrees Celsius to melt it, and then you need to make it cool it suddenly to make it an amorphous state, and also boil it with concentrated sulfuric acid. And that is how you can dissolve beryllium ores. And also it involves a lot of a process to emit particles. So this all pose the difficulty and challenges in terms of the economy and safety. So we try to focus on this process by utilizing microwave to cause internal heating to make it more efficient. This shows the advantages of internal heating using microwave. For example, in the case of external heating, the radiated heat will go through the process of radiation, convection, and conduction. Through that, the heated object will be heated from the outside. But on the other hand, when you use microwave internal heating, especially when heating objects that are polar as water molecules, then the molecules heated will be subject to the force of fields and vibrating greatly in accordance with the wavelength of microwaves. And that is very efficient, energy efficient way to enable rapid and uniform heating. This kind of approaches are used for a reduction process of some refinement of the materials, but they require a 1000 degrees Celsius or higher high temperature. And we, instead of high temperature melting, we wanted to come up with an approach using chemical dissolution process and utilize microwave for that purpose. Here, I'd like to show you how the chemical dissolution treatment can utilize a microwave treatment using some video to you. First, we are going to crush beryllium ores. And then we will mix crushed beryllium ores and alkaline agent to conduct microwave heating. The temperature of the sample is lower than 250 degrees Celsius. After the heating, we'll wait the sample to cool down and add acid to the sample. This will enable the total dissolution, complete dissolution of polysoluble beryllium ores. As you saw in the video, by combining chemical dissolution treatment as well as microwave heating, you can achieve low temperature and short time dissolution of the ore, and the required energy, consumed energy, would be 1/1000 to the conventional method, significant decrease. And also the dissolution process can be conducted at the room temperature and the normal pressure. That is something we validated through this technology. And this kind of technology can be used for beryllium ores as well as rare metal ores such as lithium ores or metallic nodules or ceramic treatment. For refinement requiring high temperature treatment, we can utilize nearly similar conditions and utilize this technology for these purposes as well. Earlier in the video, the sample amount was has a standard mineral of 1 gram or less, but right now, together with a company called Microwave Chemical, we are conducting joint development and utilize a bench equipment we have in the Rokkasho Fusion Institute. And we have succeeded in low temperature dissolution with the one batch of 100 grams or so using lithium beryllium ores. We've succeeded in dissolving these ores using this technology. And this graph shows the result with the lithium ores. As you can see, the capital expenditure, operational cost, as well as CO2 emissions can be significantly reduced compared to the traditional method. Therefore, in the case of beryllium, we've been importing beryllium ores from the United States to make it into materials. But when we can practically utilize this new technology, we can enable power-saving energy refinement technology, and also we can import various polymetal nodules or ores and refine these within Japan and provide metal materials. And also we can utilize this technology for the purpose of metal refinement coming from recycled home appliances, which is called urban mine. This will greatly contribute to the realization of sustainable metal resource circular society. For that purpose, this fiscal year, we QST employees founded Miresso, a QST-approved startup company. Miresso will be focusing on the manufacturing sales of beryllium and its compounds, as well as licensing consulting business on low temperature, enabling low temperature process for a manufacturing process. And also this company will be greatly contributing to the fusion energy utilization by stably supply a nuclear fusion blanket functional material such as beryllium, as well as realize carbon neutrality through the power saving of a high temperature treatment process. As Mr. Baba has mentioned, mentioned earlier, SBIR and the nuclear fusion field, the Mireso made an application and the demonstration of low temperature refinement technology. The theme was adopted for this program, and we have been able to show a great start to enable social implementation of a nuclear fusion technology. And we've been talking about beryllium here, and would like to move to a tritium and lithium from here on this slide.
So I will explain the current status of material. And as you know, lithium is as an expansion of EV market, the demand is going through the roof. However, materials are all imported. And for the demo reactor, we would need 100 tons, and we need to update or exchange every 4 years. And the lithium currently in circulation comes from salt lake brine or ores, but brine requires drying in the sun for a year in a place like South America, so it takes time. And also it depletes water, and there are concerns for destruction of nature. And on top of that, on the ore, as I explained later, that we need to process with high temperature, and with the high temperature that is monopolized by China, like roasting processes and calcination processes. That's all monopolized by China. But the lithium is lithium 6 and 7 exist in nature, but the lithium 6 is only existing 7.6% of natural lithium content, and we must enrich it 90% for design purpose. Therefore, in order to stable secure lithium 6 for Japan's demo reactor, it is first necessary to demonstrate lithium recovery technology from seawater and others source while responding to rapid increase in demand for lithium, such as in EV market. And to that end, for this reason, we developed the ion conductor lithium separation method. And we are proceeding the development, and it's called LISMIC. About LISMIC, as you can explain, it is explained here. In the middle, we play ion conductor, and then the lithium, and we have liquid. The lithium, we apply liquid on the both side and apply a voltage, and then on a high purity, we can recover lithium, only lithium, and this ion conductor lithium and absorption process, absorption treatment to the surface of ion conductor, and the transition from the basic research stage to the pilot plant stage is now in sight. So this figure schematically shows the internal crystal structure of the ionic conductor, and when vacancies are created as shown in the figure, lithium jumps through the vacancies as ions. So it is thought the only lithium can be transferred with high purity. So by 2030, as shown in the figure, it is predicted that supply-demand balance of lithium resource will collapse around 2030. So we hope to quickly realize the social implementation of this LISMIC technology, not only for seawater, but also for recycling and lithium batteries and recovering lithium from salt lake brine. Now about LISMIC technology that I just explained, the recovery process. I like to show you this video to help you understand how this is performed. This is the ionic conductor, the membrane, the separate lithium, and the ionic conductor is placed on top of the electrode, and on top of that, the device is assembled by placing the electrodes on top of the ionic conductor. So this is the world's first lithium recovery device. The device is filled with lithium solution and pure water as the recovery solution. The recovered solution is then sprayed with carbon dioxide gas. When carbon dioxide gas is sprayed, a white precipitate is formed, and this white powder becomes lithium carbonate, the raw material for lithium-ion batteries. So that video that we just saw, that's how lithium technology is used to recover lithium. Those pictures, using the used lithium technology was applied to recycle lithium-ion batteries. The device in the center is a stack-type test apparatus using 20 ion conductor membranes of about 5 centimeters square, as described above, which can recover 1 kilogram of lithium per year, demonstrating that ultra-pure lithium can be recovered in a single separation operation at less than half the import price at the time of evaluation. So this device, using that device at the plant site lithium recovery, and with this process we can recover at the less than half of the import price. And so this is in addition we obtain prospect of achieving recovery cost of 1/3 of the import price lithium at the time of application to Salt Lake brine. Which I will explain a little bit later, but in this arena we were able to establish a venture company. And on the other hand, as introduced at the beginning, lithium-6 enriched to 90% is necessary for efficient blanket production of tritium, and it only exists in 7.6% in nature. It's a strategic material as well, so importing large in quantity is really difficult. However, in the existing technology overseas, such as enriching lithium-6, they use so-called mercury method, and this method cannot be applied in Japan due to some regulations. Therefore, we need a separation technology that is unique to the unique Japan. And let's make. This graph shows experimental data showing the lithium and lithium-6 and 7, and the quantities or mass is different. So the transfer is the way they transfer is different. So we can use that nature to test the properties. This graph, as I show you in the video, on the left-hand side, we have a lithium, natural lithium, and we add a solution, and using lithiumic recover. And once it's recovered, the enriched lithium-6 is achieved. As you can see that this separation case is using mercury method. It's same as we can yield the same result as using as mercury mercury method, but to achieve a higher separation, lithium-6, we performed simulation, and using those experiment, the higher separation factor using cascade, and we can improve enrichment, and the cascade model was optimized then to achieve 90%. And that's the technology development that we are working to achieve 90% by optimizing multi-stage cascade. But first of all, we have to be able to recover lithium, and that's the first thing first. And as I mentioned earlier, the lithium, to secure lithium resources, established company, Listy. This is a QST approval venture company. This company is designed to recover lithium. And the first industry wastewater is the first target. A wastewater that will first target industrial wastewater and manufacture and sell a lithium recovery unit with a standard treatment scale. And then the unit will then be applied to recycling using lithium batteries and recovering lithium from salt lake brine and ultimately from seawater. So LISMIC, through these efforts, we aim to be a bridge company that connects the decarbonized society to the next generation by implementing LISMIC in society and contributing to the promotion of EV and fusion. So that's what LISTI is aimed for. And so SBIR funding is secured, and we were able to launch this business. And those pictures then start up two companies. Those are pictures of Mires and Listy, and satellite office was landed by Rokkasho. So this is the outside of the office. This is the picture of business launch ceremony, and with the local government or local communities have placed significant expectation on us, and we are also deeply heavily supported. With the funds we received, we were hoping to be able to use those technology, apply in technology in society and implement in society. Before I close, this is what Rokkasho is trying to achieve. This is the vision that Rokkasho wants to achieve, and with the demo reactor, beryllium rare metal recycling plant, and lithium recovery recycling plant, and fusion industry is something we would like to create, and this is the future of us that's composed of different plants and different functions. And Mr. Baba and others have been presenting what we have been doing, and fusion and energy fusion strategy is extremely important. But our fusion technology, the Cabinet Office, and the Fusion Energy Innovation Strategy and QST, we all need to come together to achieve this vision. And I would like to continue to work on this with everyone. Thank you very much for your attention. And Mr. Hayashi, thank you very much for your presentation. That brings us to the end of keynote lectures, and I would like to take a quick break. The next program, the special lecture, will start at 4:10, and please be back before 4:10 or 4:10. Thank you.
ITER BA 成果報告会2023にご来場の皆様にご案内申し上げます。まもなく ITER BA
Thank you very much for participating in ITER Annual Symposium. We will be starting the part 2 of the symposium shortly. If you're at the lobby, please come inside the hall and have a seat, please.
お待たせいたしました。ITER BA 成果報告会2023の後半の部を始めさせていただきます。最初は 特別講演です。本日ご講演をいただきます国中仁様のご紹介をさせていただきます。
Thank you for your patience. Now I'm pleased to begin the second half of the annual Symposium 2023 on the ITER activities. Let's begin with a special lecture. I would like to introduce today's speaker, Dr. Hitoshi Kuninaka. Dr. Kuninaka graduated from the Graduate School of Engineering at the University of Tokyo in 1988 and obtained a doctorate in engineering. He then joined the Institute of Space and Astronautical Science of the Ministry of Education, Culture, Sports, Science and Technology. Now, the Institute of Space and Astronautical Science of the Japan Aerospace Exploration Agency, where he was served as professor since 2005 and Director General of Institute of Space and Astronautical Science and Vice President of Japan Aerospace Exploration Agency since 2018. His specialty is aerospace engineering, especially electric propulsion engineering, and he was awarded the Medal with Purple Ribbon in 2021. Today, he'll be giving a presentation titled Hayabusa and Hayabusa 2 Asteroid Exploration, Realization of Space Navigation by Ion Engines. Dr. Kuninaka, please. Thank you very much for the introduction. Today, I would like to talk about our activities, and I am very honored to be able to be given this opportunity. I am Kuninaka. I'm the Director General of the Institute of Space and Astronautical Science. And at our institute, including Hayabusa and Hayabusa 2, we have been doing asteroid exploration. And now I'd like to talk about these activities. And this is the table contents. At first, I'll be talking about electric rocket. I would like to talk about the engineering aspect and the models. And this technology uses plasma ion engine with the development of electric rockets. Diagnostics have been also researched, and I would like to talk about that. And then I would like to talk about Hayabusa 1, the first generation, and successor Hayabusa 2. I would like to talk about these two. And lastly, I would like to talk about the future plan. So first of all, the technologies for rockets. This is the principle of space. There is an equation for rockets, 12-key equation. And this rocket equation is expressed like this. Delta V is for satellite, how fast a satellite can go. And with more velocity, further the rocket can go. Not only that, when they can also come back to the Earth as well. Delta V should be as large as possible. And so our ambition is to create as big delta V as possible. And in order to make the velocity big, we have this M-prop propellant. And if M-prop is larger, then delta V can be bigger as well. But if M-prop is too big, the rocket system or the exploration system can become very big with a lot of fuel. Without increasing fuel, if we can increase delta V, what is the option? VEX, this is another parameter. VEX is exhaust velocity. And if we can make exit velocity faster, then delta V can be made bigger linearly. This is the rocket equation. So to have a faster jet, then fewer fuel can be used. And so in terms of the chemical rockets, chemical energy is used to make a high temperature gas, and then in this way, theoretically speaking, the upper limit has been already reached. 3 kilometers per second is the upper limit. You can't make a jet injection faster than this with chemical rockets. And also, there is another one, electric rockets. Using electric rockets, static velocity or other method make it possible to give energy, and that way you can actually achieve 30 kilometers per second. So from 3 kilometers per second to 30 kilometers per second, you can have a 10 times fast. So with the same amount of fuel, delta V can be made 10 times big. This is what this equation shows. And this is one of the electric rockets, ion engine type. Ion engine is creates ion by electric discharge, and then using electrostatic acceleration, it creates a jet injection of 30 kilometers per second. This plasma is very different from the fusion by that you are familiar with. When the lower the temperature is, the better. That's what it is. What's necessary for rocket propulsion should be one monodirectional locomotive. And in response, a rocket can move. So you don't need high temperatures. What I mean is random heat velocity is inherent. So if random energy is given, then energy can be lost. So we want to make plasma that is of low temperature. That is what is needed for ion engine. To the method for creating plasma, I wonder if you are familiar with this. We have Kaufman type, or this Kaufman is Harold Kaufman, NASA engineer. Harold Kaufman, in an early stage, created this DC discharge ion source from filament by having DC speed, and they created a ionization. And this is the ion source. From that, from Kaufman ion source, we have filament and positive and negative electrodes, electrostatic in Kaufman. And also, in order to confine electrons, we have like a vertical magnetic field as well. And from that, we also have ring cusp type that was developed in the US. That means on the wall, we have a lot of permanent magnets. And by that, we confine electrons. This is ring cusp type. And in Europe, not using DC, but RF ion source is also used. And also, we try to increase the frequency even more to have the microwave type. That's what we have been researching on. And why do we research on microwave type? It is related to the longevity. This chart shows xenon and molybdenum sputtering. On the horizontal axis, ion collision energy, and on the vertical axis, sputtering rate, and 50 volts is the threshold. And if this becomes the effect of wear out due to the sputtering phenomena, resulting in a short lifespan, and we want to create the 1 to 2 year of operational rockets. So if the electrodes wears out because of sputtering, that can be a deciding factor for this device. And it is actually possible that the wear begins at 50 volts. What is important is divalent ions. And divalent ions is less than 1%, but because of this, wearing out starts, and it is really difficult to have the ion engine to be able to continue operation for 1 or 2 years. And so the heat electrons created by the positive electrons to go and then create a low temperature ion, and created ion can go to electrodes, and electrodes wear us out. That is when this ion engine wears out. And if you don't use these colored parts, and if you have the microwave type, that can be promising. That's why we decided to develop this. Microwave discharge is electrode-less, so that doesn't have any factor for lowering the shortening the lifespan. And electrons are trapped in a mirror magnetic tube formed between a pair of magnet tracks. As electrons move back and forth, they pass through the ECR region multiple times and are gradually heated. 0.6 eV heat input pass. Since electrons pass through the ECR region 4 times in one round trip, it takes about 2.4 electron volts, and 10 round trips can obtain the energy required for collisional ionization. So that is the enough amount. And if I explain this by energy distribution, on the horizontal energy distribution, energy to produce PE for DC discharge, and vertical distribution. And we have, in case of DC discharge, electrons with Fermi potential in solid electrode are emitted into vacuum, then heated by DC electric field, then high energy electrons are generated, and then collisional ionization happens. And then the electrons that lost energy are now are going to low energy electrons. But in terms of microwave discharge, they use the low energy electrons and to create a high energy electrons, then collisional ionization happens. And so low energy electrons are recycled. So the energy amount that has to be input can be lower. This is a big comparison between microwave discharge and DC discharge. And for this ECR type, Dr. Inutake of the University of Tsukuda gave us a lot of lecture and showed us gamma 10 research. So this is microwave ion engine overview. Just a side note, I would like to talk about this. Ion engine creates plasma and inject ion. If you look at space, space doesn't have walls, so injected ions can go as far as it can go, and it cannot create circuit for current. So you have, along with the ion current, electrons are also emitted, and that will close the circuit. So ion engine, at the same time as ion current, electron currents are also emitted. But electrons are very light, and it will not contribute to propulsion. So creating electrons has a minus effect for ion engine. So in order to further develop the technology, negative ion, if negative ion can be emitted, then negative ion as well as the locomotion can be created. So Xc positive plus C60, positive and negative ion beam engines. This is something you can utilize. To develop this, Dr. Ando of Tokyo University lectured our students in terms of positive and negative ions. And cesium was coated to create a negative ion, and for positive ions, magnetic filters removed the ions. But using cesium was a lot of work. So we did a lot of research, and fluorine C60 minus ion was actually used for this research and experiment. And this is fluorine C60 negative ions, and I have a lot of xenon microwave positive ions. So fluorine negative ions and xenon positive ions were combined, and at the same time, thrust beam was emitted to create even more thrust. And it was the first achievement in the world, I believe. The absolute amount is very small. Beam is like only 3 millimeter ampere plus 3 millimeter and minus 3 millimeter ampere. And this is when thrust was created. And I think this is something we can collaborate with experts on fusion. The next thing I'd like to talk about is diagnostics. Low temperature plasma, for the measurement, we use Langmuir probe. For microplasma, if you insert metal probe, then the electric field is disrupted significantly, and we can't you can't have good data. So laser absorption spectroscopy or laser inflorescence are something we have been developing. Laser absorption, for that, we have only this data. As it is difficult to measure with spatial resolution, so we try to be creative. Fiber probe, at the edge of the fiber probe, we try to put light by optical fiber inserted into the ion source for measurement. Signal decreases as optical path length becomes shorter. So by having the differential, we have the local plasma parameters. This is what we created, the probe. On the horizontal space and on the vertical axis, you can see the density. And also, LEAF has the special resolution, so we can have microplasma research and development this way. And also, at the center of the probe, we attach the EO element, so that the refractive index can be changed by the microwave electric field. This is also something we are working on. So in this way, microwave ion was used for Hayabusa exploration. So I would like to, the Hayabusa and Hayabusa 2, they departed Earth and arrived on Itokawa and Ryugu, and they took samples and they came back to the Earth and delivered samples, and that was the very, very long haul journey for them. And that was because we looked at this rocket equation, and because we decided ion engines to make the very small 500 to 600 kilograms ion engine to go back and forth between the Earth and asteroids.
In the United States as well, they were inspired by Japan, and they decided to conduct a project of OSIRIS-REx asteroid sample return project from behind from Japan. But the United States utilized chemical rockets. That means they need significant amount of fuels. All the total weight exceeds 2 tons per each probe. But Hayabusa 2 weighs 600 kilograms. However, the US 2 tons, and also the scale of the project was 1.2 billion yen, and based on the exchange ratio, that would be a significant amount. So that was very big mission in the United States. However, in Japan, by strategically utilizing ion engine, we've been able to create very lightweight and efficient probe and to achieve the return to Japan, going back and forth from the asteroid. And this is Hayabusa 2. In 2014, we launched Hayabusa 2, and the target asteroid Ryugu. We arrived at it and collected some samples. In 2020, Hayabusa 2 went back to the Earth. For the Hayabusa 2 project, I served as the project manager, engaged in manufacturing of the probe, and from Tanegashima Space Station, I myself pressed the button of a launch. Preparation completed, and I pressed the button to launch the probe by myself. The explorer departed from the Earth and going to the opposite end of Sun and made a rendezvous to the asteroid and landed. And between Sun and Earth, that is the one astronomical unit, and to enable a telecommunication, it would take 8 minutes. So with this distance from the asteroid, you need 4 astronomical units to ensure communication. When we send out a message from the Earth, you can receive the response 30 minutes later. So that is the distance we succeeded in the rendezvous and atomic landing, as well as collection of sample going back to the Earth. This is the samples coming from asteroid Itokawa and asteroid Ryugu, as you can see in the slide. They are very small asteroids, so we took the picture for the first time using the probe, and you can identify what they look like. Even when you use telescope from the Earth, you cannot identify these kind of shape and visuals from the Earth, but that is the challenge we took out. And ion engine of Hayabusa 2 broke down. Excuse me, Hayabusa 1, but in case of Hayabusa 1, ion engine A broke down, B, as well as C and D. All of them broke down. But ion source and a neutralizer, these are the components of ion engines. So ion source A was broke down in the case of Hayabusa, but neutralizer was intact. And thruster B, the neutralizer B was broke down, but ionic source B was okay. So we had the bypass circuit combining the neutralizer A and ion source B. Combining that, we were able to produce the propulsion of Hayabusa 1 coming back to Japan thanks to this. In 2010, June 13th, the capsule was collected in the Woomera, a sand dune in Australia. You can see a bright spot in the sky in the video. This is a probe, 12 kilometers per second, and entering the atmosphere. Due to the collision with the atmosphere, you can see temperatures is being increased. The probe is distracted. You can see the purple color. This is a light of xenon, and you can see the color is turning orange. This is from the lithium used for the battery of the probe. The in complete destruction, but something is flying in the sky. This is the return capsule coming from the probe. It can withstand a collision with the atmosphere and high temperature. It safely landed on the Earth, the desert. And for Hayabusa 1, as everyone is pleased, there were so many movies and films made out of this, and the failure bionic engines are well described in all of these films. If you are interested, please watch them. And within the capsule, we had so much gravels. This is from asteroid Ryugu, the materials from the asteroid. And scientists across the world share this in conducting analysis on the material. 5.4 grams is a very significant amount coming from the asteroid. And the scientific outcomes were covered by Science and Nature, prestigious scientific magazines, and not just papers, but also you can see on the cover of these magazines, the Hayabusa's photos and pictures were on the cover of the scientific journals. So this has attracted so much attention from all over the world. Last but not least, I'd like to touch on future projects as well. We are proceeding with further space exploration. We are utilizing Ion Engine, our third mission, what is called Destiny Plus spacecraft. This is equipped with 4 Ion engines going to the asteroid Phaeton. It is under production. It will be launched in 2025 in the plan. And this is on a different topic, but we are operating a smart lander for investigating moon, which was launched in last September. It is moving and falling to the moon, and last night it entered the circular orbit of the moon, and it will go down closer to the moon, and 20th this month, and at midnight, early morning Saturday, this will be landing on moon. How it will land on the moon? We are conducting a lot of outreaching activities on our website. You can see how Slim will land on the moon. This is a CG video. If you are interested, please check this out. Slim, a moon landing 303 degrees CG. This is something you can see, or you can use this QR codes on the slide. Please use your smartphones to scan, and then you can reproduce CGs on your smartphone. This is how it looks like. We are on the surface of moon, and when you look up, you can see the Slim is trying to landing on moon. You can see the white light. This is the thruster to adjust position, and you can see main thrusters in the center. And by utilizing ejection thruster, you can see it will safely land on the moon. We can see the footprint on the surface of the moon. This is how it is elaborated. I would kindly appreciate your support and interest in this matter. And at the entrance, you can see Hayabusa 2 and Slim stickers are prepared for you. Please pick them up. And the next slide, Destiny 2, Hayabusa 2, and future project Slim. I've touched on these topics But not only that, we'd like to make a solar system exploration in Mercury. We are sending probes, and around Venus we are sending out some probe as well. And also we've sent so many satellites in various planets. And also for Mars, we are proceeding with MMX2 and asteroids Hayabusa 2, a Destiny Plus, in Mercury, Jupiter, and Saturn. And together with NASA, the United States, we are co-developing probe and explorers. So many explorers will be spread across all the planets across the solar system, and by integrating the information coming from all the explorers, we'd like to look into the origin of space as well as the life. That is what is called deep space fleet we are trying to create in the solar system. This is the activity we are trying to create within the solar system, and by utilizing this 4.6 billion year history of the solar system, as well as the origin of life, will be a further unveiled. I would very much appreciate the kind support on this. And with that, yes, I've exhausted all the slides. Thank you very much for kind attention. Mr. Kuninaka, thank you very much for presentation.
Next, we move on to technical session. To make good on fusion energy as early as possible, we need everyone's participation from industry. And today, technologies in Japanese industry, how they can contribute to ITER program or ITER project in the BA, and also fusion, nuclear fusion reactor development, how they are contributing. We have invited 6 companies to present. And first of all, from Arikawa MFG Innovation Promotion and the Molding and Material Development Team, Mr. Chief of Technology, Mr. Hirai Masaaki, will give us a presentation. Thank you. Mr. Hirai, please take the stage. I am Hirai from Arisawa MFG. Thank you very much for your introduction, and thank you very much for giving me this opportunity to present. And for my presentation is titled Research and Development of Insulation Materials for ITER TFPF Coils. First of all, let me give you an overview of Arisawa. It was founded in 1909. We were now in our 116th year company with a history of more than 100 years. So we have a long history, and our headquarters are located in Niigata. And when the company was founded, we began with braided cores and knitted fabric called button lace. And as shown here, and we have long years of experience, know-how in weaving. Therefore, our core technology start with weaving technology, followed by pre-preg processing technology to attach original resin, thin film, and high precision coating technology and molding technology to form these materials. We were a manufacturer of secondary intermediate materials that support various fields with these technologies. And I will now give an overview of the development of insulation materials for TFPF coils adapted for ITER. And we have been supplying insulation materials to heavy electric machinery manufacturers and rolling stock manufacturers using weaving and coating technology method. And we have received approval from ITER organization to supply a total of since 2024 and 2021. In total, 280,000 square meters materials. That's how much we have provided, and we are waiting for the operation to start with excitement. And regarding the composition of product outline we developed, it is an insulating tape consisting of S2 glass cloth and polyimide film laminated with resin. And for PF coils, the resin is epoxy-based with TF coil, mixture of cyanide ester and epoxy is used to provide additional radiation resistance. And there are 3 points in development. First is the neutron wire resistance, and which is the most important factor. Second is windability to coil conductors, and the third vacuum impregnation at the third region. And this table compares the characteristic of our developed product with those of others. In order to satisfy 3 development points that I just mentioned, we first designed the optimal fabric and weaving technology using boron-free ST yarn, which is the resistant to neutron radiation as the base material design, and in parallel, we designed the most important resin. And then cyanide ester resin with excellent neutral radiation resistance was selected as resin. And then not just the design and the handling, and we select the material. And for as an insulation tape in a high temperature or any condition, we laminate with polyimide film, which ensure minimal change in electric properties, in insulating properties in circumstances. So those are the characteristics that supersede others. And I like to explain neutron radiation resistance. This is you see that vertically comparing our product. And blue is before irradiation, red is after irradiation. As a result, the other company material was just within the required specifications with a post-irradiation degradation of 16.3%, but our material has sufficient margin compared to the specification, and the post-irradiation degradation is 8.85%. We believe that this result a major factor that we were selected. And the tape has been adopted as an insulating tape for TFPF coils in ITER, and now is under construction in Cadarache, France, and we are very proud of that achievement. Next, I like to explain the status of research related to the demo project. As you all know, a special team for demo reactor design has been organized under the policy of Minister Education, Culture, Sports, Science, and Technology in cooperation with industry, academia, and government, mainly led by QST, and we are participating in this project. So this team is led by Professor Nishijima of Fukui University, and we have started research in radiation-resistant insulating materials. The purpose of this research is to provide direction for the selection of radiation-resistant insulating materials, and basic material composition is the TFPF coil insulating tape with polyimide film used ITER. On improvement based on this tape, we are also considering the following 2 points to be solved insulation tape for demo. And the first is the verification of the possibility of polyimide film reducing interlaminator shear strengths FRP, and the second is the as fundamental aspect elucidation of insulating properties of GFRP. So first, let me talk about the practical aspect of A. We place the polyimide film in the center of a specimen with notches, and then measure the shear strength of the specimen under compression using the nail jig devised by JAX, as shown in this photo. And that this nail jig was designed specifically for compression testing of CFRP, and since it can apply load while restraining the edge of the specimen, buckling of specimen edge does not occur, and the specimen can be a rupture and highly accurate compression. So using that dig, the test result using the fixture are shown in this table. So by using polyimide field, we need to indicate that when using laminated with polyimide film, it is necessary to assume lower interlaminator shear strengths than those without polyimide field. And next, B is that we believe that in the past, material selection has generally focused on the electric breakdown voltage on BDV under strict conditions, and we performed test, and therefore to address the question of the BDP under stress, we conducted a BDP test with needle electrode placed in the compressive shear stress area in the center of specimen as shown here. So I will explain that more later. And this is the result of the excess voltage. The vertical axis is represent voltage, and the horizontal axis is represent load, which can be also be set at a certain stress. Red is room temperature, and blue is under LNT. As you can see, that BDP is maintained under certain compressive shear stress, but when the stress exceeds a certain level, the BDP decreases. At the last rupture stress, there is a macroscopic defect because of the fracture, but below that stress, the BDP decreases despite the absence of macroscopic defects. This is the fiber and the resin that made up RFP, and this makes the insulator rupture, and under certain after a certain point that there's a macroscopic defect fracture, and under LM, cohesion of material improve and absolute value stress increase, but behavior is the same. In conclusion, at Arisawa, we would like to summarize. Arisawa is capable of providing materials that meet your needs using our core technology of weaving, coating, and forming. We are also capable of designing and supplying materials with excellent insulation, radiation, and I wish you the success of ITER project. And thank you very much for your attention. Mr. Hirai, thank you very much for your presentation.
The next speaker is Mr. Hara Kensuke, Technical Expert, 2nd Engineering Department from Kyocera SOC Corporation. Mr. Hara, please. Thank you very much for the introduction. I am Kensuke Hara, Technical Expert, 2nd Engineering Department of Kyocera SOC Corporation. And thank you very much for giving me this opportunity to give a report. I would like to talk about the development of collection optics for Thomson scattering system in JT60SA. First, I'm going to tell you 3 things. First, Kyocera SOC Corporation is a manufacturer of optical products. We custom design and manufacture optical units such as objective lenses, as well as optical elements such as mirrors, filters, and lenses, and we sell lasers on our catalogs. Second, our company's involvement with fusion began in 2009. This was because the person in charge of Thomson scattering measurement and the president of a company at the time used to work together. Third, we were involved in the entire process from conceptual design to manufacturing of the collection optics for the JT60SA Thomson scattering system. These are what I would like to talk about today. This is the table of contents, introduction of a company, explanation of Thomson scattering system, development of the collection optics, and summary. Let me briefly introduce our company. These are our products. Our company name is this, Kyocera SOC Corporation. We are in Yokohama. It was established in 1954 and is celebrating its 70th anniversary this year. It is a manufacturing company with 275 employees, 70% of whom are directly involved in manufacturing, such as engineering, manufacturing, and inspection. Now, I will explain about the Thomson scattering, but before that, these are the products. These are the 4 products and application field. There are 3 types of products: optical units, optical elements, and lasers. Optical units are characterized by ultraviolet, visible, and infrared compatibility, high specification, and customer order compatibility. Optical elements are of by high precision, high damage resistance, and customization, while lasers are characterized by visibility, compactness, and high reliability. Our products are used in the fields of space and defense, industry, and life science. In the space field, our products have been installed on satellites such as Kaguya, Hayabusa, and Shikisai. In the industrial field, our products are used in semiconductor exposure and inspection systems, laser processing machines, and so on. In the life science field, our products are used in biological microscopes, flow cytometer, and DNA sequencer. Now, I will explain about the Thomson scattering collection optics that we have been working on. This shows the positioning of the collection in optical system. You can see the collection optics shown as figure 1 and number 1 in the figure. When a laser beam is shot into a plasma, the laser beam is scattered by the electrons in the plasma. This is Thomson scattering. The role of the collection optics is to focus this scattered light. By analyzing the collected data, the electron temperature and density in the plasma are measured. The collection optics in this project is located at the P2 horizontal port of JT60SA. Let me now talk about the collection optics. This collection optics system focuses on Thomson scattered light emitted from a measurement range of 1,392 millimeters on the laser optical axis onto 46 fiber bundles corresponding to the measurement points. There are 3 features. 1, wide wavelength bandwidth. The wavelength bandwidth of the Thomson scattered light to be focused is 480 to 1,100 nanometers. Complex spatial arrangement is 2. The optical system is arranged in a 3-dimensional twisted relationship with respect to the measurement range. 3. Narrow layered area. The optical path is bent by 2 mirrors behind the lens to keep it within the restricted placement area. And there are 9 specification items as shown here. Now let me talk about the development of collection optics. Here is an explanation of the design flow. We optimized the design parameters and lens design, then bent the light beam with a mirror in the back focus space to secure the placement space on the image side. We then proceeded to the structural design. The figure shows parameters. In blue are requests for parameters. On the left, 2 trade-offs for parameters are shown. One is the trade-off between the measurement specifications and the lens. The parameters are correlated, so we looked for a good balance. The other is a trade-off between the lens and the placement. Since all but one of the requests are completely opposite, we tried to find the last possible compromise between the 2. For these trade-offs, we went back and forth from parameter optimization to structural design. This is the lens system. Based on the Ornostar type of camera lenses, we followed this policy for the Seidel aberration and 2 chromatic aberration. The design resulted in this a 5-element system with a maximum lens diameter of 227 millimeters, f number 2.5, and a focal length of 352 millimeters. Resolution results are shown here. Over the entire measurement range, the spot diagram is less than 0.38 millimeters RMS, and the encircled energy is less than 0.47 millimeter radius, with 90% as the threshold. Transmittance averages 74% over the entire measurement wavelength range. This is the structure. There are 4 fields in terms of requirements. Regarding functions, a double frame structure is used to retain the lens that can guarantee imaging performance. The structure also has 3 rotational axes as an adjustment mechanism for the lens system, and 1 linear and 1 rotational axis as an adjustment mechanism for the image plane. Regarding materials, a large amount of insulating glass epoxy is used to minimize eddy current during disruption. Also, the metal part is structured to cut a loop across the insulator. These photos show the manufacturing process. We assembled the lens while adjusting the eccentricity. We then installed things such as mirrors and adjustment mechanisms and moved on to the overall assembly. We did 2 types of inspection. In inspection A, light was directed from the measurement point to the image plane to measure resolution and transmittance. In inspection B, light was directed from the image plane to the measurement point, and the position and resolution on the screen were checked. Let me recap my presentation. Kyocera SOC designs and manufactures custom optical units and optical elements and sells lasers on catalogs. The project's collection optics has 3 features. 1. Wide measurement range and wavelength bandwidth. 2. 3-dimensional imaging relationships. And 3. Narrow layout area and large aperture lens. In developing the collection optical system, we optimized design parameters, designed optics, layout, and structures, and completed manufacturing process last year. That's it. That's all. Thank you very much. Mr. Hada, thank you very much.
続きま
Next, we'd like to invite Mr. Honda Hidetaka, JT60SA Project Group Leader, Construction Business, Construction Department, Osaka Headquarters, Plan Department.
Honda 様、よろしくお願いいたします。
Mr. Honda, the floor is yours. Thank you for your introduction. My name is Honda from Korea. Thank you very much for giving me this opportunity. I'm very honored. So with the title Participation in JT60SA Construction, I'd like to talk about our initiatives and activities about nuclear fusion. This is the content of my presentation. I'd like to introduce my company as well as our track records related to nuclear fusion. First, this is a corporate introduction. We were founded in 1946 with an employee number of 829. Our company works as an engineering company, offering the power-related business to support stable operation of various power plants, and we engaged in 8 business pillars. This shows 8 businesses we are engaged in: nuclear, construction, machinery, electrical facility, power plants, overseas development, and engineering. These are 8 businesses we are doing. The slide shows our locations. We have 47 offices within Japan and 3 overseas offices and locations. This slide shows a list of renewable power plants we are deploying In total, we have the power capacity of 19 megawatts in total. Next, I'd like to talk about what we have achieved in scientific research field. In 1978, we participated in the Kyoto University Heliotron E nuclear fusion experiment, and in 1994, we participated in the construction for NIF's large helium A device, and in 2012, we participated in JT60SA project. In the field of accelerators in 2008, we installed spring-gate X-ray free electron laser, as well as the construction in 2022 for next-generation synchrotron radiation facility. For large helical device and next-generation synchrotron facility, I'd like to briefly explain to you. First, a helical device. We manufactured and installed two vacuum pipings. One is vacuum piping system for vacuum vessels to enclose plasma, as well as a vacuum piping for cryostat to insulate the heat plasma from the superconducting magnet. And also not only manufacturing installation of vacuum piping system, we are engaged in the installation of control console and control board for operation, as well as compressed air system to switch vacuum valves. And also we install underground suspended frames for wiring and pipes. We are engaged in the installation of various devices and systems related to vacuum piping system. The next one is about synchrotron radiation facility for the next generation. On this linear accelerator and 509 megahertz, radio frequency cables were installed, and required installation accuracy was 0.05 millimeters, but we were successful in installing that. From here onwards, I'd like to talk about the track record for JT60SA for Naka Fusion Institute. We conducted various construction works for Naka Fusion Institute. As you can see here, I'd like to talk about four things: a vacuum piping system for the cryostat and cooling water piping for the diverter, as well as baking gas circulation piping, room temperature busbar, and instrumentation cable trays, as well as control panels and power supply panels. These are what I'd like to talk about, and this slide shows the bird's eye view of JT60SA and arrangement and placement of each device we installed. The first one is vacuum piping system for cryostat. This was manufactured at the factory at the factory we conducted manufacturing assembly of the system, and then we conducted performance testing as well as helium leakage testing. In the helium leakage testing, we've achieved the vacuum level of 10 to the power of -4 Pascal. And we put into 3 parts and imported into the site and installed and reassembled at the site. And turbo molecule pumps and control boards for the cryostat vacuum piping system, we conducted the magnetic shielding and designed it and installed it to prevent them from a magnetic field from T60SA. And the cooling water piping for diverter and baking gas piping. And these are the cooling pipes, and we are engaged in the installation of the piping for cooling to create a circular shape. As you can see in the slide, we manufactured it and installed it. And the first wall of the vacuum vessel will be baked to 200 degrees Celsius. So for that to be achieved, we've created the external piping, manufactured and installed it. And for cooling and piping, we conduct maintenance for existing heat exchanger and pumps as well. The third one, this is about room temperature busbar. To supply power current to the superconducting magnet, we manufactured and installed a room temperature busbar from the power terminal on the wall to the superconducting lead of the coil, and 25.7 kilowatts at the rated power for toroidal coil and 20 kiloamperes for toroidal coil. This is called busbar, but shaped like a cylindrical void, and you can run cooling water inside. Fourthly, instrumentation cable tray. And this is what we installed, the cable tray for a control panel, as well as a information signals will be sent through this tray, as well as a control panel. Both were installed by us as well. And also what I'd like to touch on lastly is a dispatch to Padova. Before the ITER and base system establishment, we dispatched people in charge of construction on site in Padova, Italy, to install NBTF at the same scale as we created in Japan. This is the summary. We leveraged our experiences in large-scale construction facilities for the T60SA from 1978 for various construction. And as you can see here, we experienced a lot of facility design and construction. We have a technology to manufacture and install a large-scale equipment at high precision, and we can offer a one-stop solution from manufacturing, installation, operation, and maintenance for various equipment devices required for fusion research facilities, and would like to leverage our strength to contribute to this world. And would like to conclude my remark. Thank you all very much. Mr. Honda, thank you very much for your presentation.
Next presentation is from Mr. Yoshikazu Toyama, the Representative Director of Shoritsu Kogyo. Mr. Toyama, please take the stage. Thank you for your introduction. I am Toyama of Shoritsu Kogyo, and thank you very much for this opportunity to give us a present. And we are a small, medium-sized company that manufactures electrically insulated processed products. And we are very grateful and honored to have participated in this Future ITER project with support and cooperation of everyone involved, even though it has been very challenging. And today's report is about Shoritsu Kogyo efforts and challenge in nuclear fusion, and the development of composite insulating materials for use in harsh environments and realization of high precision machining. And so please look at the right-hand side. That's the content. My presentation first. Let me give you an overview of our company. And our company has been around 77 years, and it has about 100 employees, specializing in manufacture and plastic cutting parts and insulated parts. We are located right next to the west side of Itami Airport in Osaka. And we manufacture a wide variety of insulated parts for large electrical equipment, mainly for major electrical manufacturers and heavy industry manufacturers. And also, we are subcontractors, so we are sort of unsung hero, but we are important and indispensable key component. So we do our work with pride. And here, as you can see in the photo, we use GFRP epoxy resin glass composite and various resin and plastic, which is difficult to cut and process, to manufacture products by machining each item with a machine tool. And we also have proven track record in the field of low temperature and superconductivity. For superconducting equipment, we have delivered components for JT60SA, nuclear fusion accelerators, medical equipment, semiconductor manufacturing equipment for universities and research institutes. The photo below shows a flax core delivered to Ono Laboratory, Graduate School of University of Tokyo, and also on the right is the helical coil winding frame delivered to Nomura Laboratory, Graduate School of Meiji University. The groove is the helical in shape. Next, I'd like to introduce 3 strengths of Shoritsu Kogyo. We value the power of our materials and products and manufacturing facilities and our people. Among these, we are building a company that can be of great service to our customer by focusing on human resource development. And as we are committed to making the impossible possible, we work while challenging difficult projects under the model of challenger to the next generation. Next is about ITER project, and today it's been mentioned a few times already. This is the ITER toroidal field coil photo of toroidal field coil. It's 18 meter in the TF coils at 16.5 meter in height, and it has 9 of them. And Toshiba Energy and Mitsubishi delivered those parts. And the yellow part is the insulating panel, will be very important. And we delivered more than 200 insulated panels of 3 millimeter thick. And this insulating panel will be a very important product as a support structure between TF coils. And in ITER, where the superconducting coils are cooled to minus 260 Celsius, these panels and their accessory will support more than 600 tons of electromagnetic force. Therefore, the panels and the accessory must have not only insulation properties, but also radiation resistance, mechanical strength, and processing accuracy required. And as for radiation resistance, the general standard GFRP material contains the boron, but the boron takes in neutrons and degrades insulation, so all the materials needed to be boron-free. And secondly, the mechanical strength of the material had to be twice that of the standard material with compressive strength of 720 megapascal minus 196 degrees. And thirdly, the entire surface of the insulating panel, which is a composite of glass fiber and resin, and is extremely hard, strong, and difficult to cut, and its thickness accuracy had to be kept 3 plus or minus 0.08 meters. And let me briefly explain the composite insulating panels. This is a composite material of special glass cloth and epoxy resin, which is completely formed by two-step manufacturing process. The development process took much longer than originally planned, taking as long as 3 years. And as a raw material, boron-free and high-strength glass fiber was required as the base material, and a special grade made in the US was used. And we used boron-free resins, including epoxy resins, which react much faster than ordinary resin, making molding very difficult. The cost, in the end, after trial and error, the cost of the prototyping was substantial, but we managed to complete the product. As a result, the compressive strength of the insulating panel was 1.78 times the required value, and thickness accuracy was well within plus minus 0.08 meter, and this product was delivered to the ITER organization under direct contract for verification. We have a direct contract with ITER, so we deliver the product and for their verification. The next is a step to realize high precision machining. We also have a manufacture insulated parts of various complex shapes. And so we provided more different parts of parts, and this is what we deliver to Mitsubishi Electronic. And in the end, TF Coil of Mitsubishi Electronic Corporation winding part contain this part, and other than that, to Mitsubishi Electric Corporation and Toshiba Energy System Corporation, we deliver all sorts of different parts. And with that, I would like to conclude my presentation regarding our contribution to ITER. Next, I'd like to introduce our customers. And our direct customers are Mitsubishi Heavy Industries, Mitsubishi Electric Corporation, and Toshiba Energy System Corporations. And we are grateful for their recognition of our technical capabilities. And we are also grateful for all the support and guidance we have received from everyone. So I like to say thank you for all the support. And we'd like to express our sincere gratitude, all of your support, and especially to Mitsubishi Heavy Industry and also QST ITER organization. Thank you very much for helping us our development. And as for the future effort, there are still issues to be addressed toward the realization of nuclear fusion, demo reactor, development of radiation-resistant insulating materials need to be more continuous and active, and high-precision machining must also be developed. To this end, we need to work private and in private and public sector, academia, collaboration, and strengthening cooperation with customers, development of human resources. We have to work everywhere. And about in the private sector, industry, academia, government collaboration, we need to deepen joint research and cooperation with QST, universities, research institutes, related companies and partners in academia, societies, and would like to participate in the Fusion Energy Forum. And as it has been mentioned here, and we would like to be actively participate in the discussion and association. And it's really difficult to achieve what we want to achieve by ourselves. And we are looking forward to working and collaborating with you. And finally, I would like to conclude my presentation by introducing our employees. So our motto is to make impossible possible, and all of us at Shorizu Kyogyo will continue to take on challenge in the future. Thank you very much for your attention. Mr. Toyama, thank you very much.
The next speaker is Mr. Ryohei Watanabe, Research Director, Environmental Protection Laboratory, Dowa Ecosystem Company Limited. Mr. Watanabe, please. Thank you very much for the introduction. I am Watanabe from Dowa Ecosystem. I am very honored to be given this opportunity. Earlier, Mr. Hayashi talked about lithium-ion batteries. And he talked about lithium. And I would like to talk about used lithium-ion batteries from the perspective of recycling and also the technical challenges we are facing. This is today's presentation content. Today, I would like to talk about our group, Dowa Group. And then I would like to talk about lithium-ion batteries. I will call you LEAP from now on, social demands and technical challenges for LEAP recycling. And lastly, I would like to talk about expectations for LISMIC in LEAP recycling. As mentioned earlier, LISMIC is lithium separation method by ionic conductor by using ionic conductor membrane. And Mr. Hoshino invented this method. First of all, I would like to talk about our group company, Dowa Holdings. It was established in 1884. Originally, we had been doing smelting and working on mines, but now we have 5 core businesses shown here. What I would like to talk about today, recycling of lithium-ion batteries, is done by environmental management and recycling business that's done by Dowa Ecosystem. The characteristics of Dowa Group is like this. This is the business model for recycling resources. First of all, non-ferrous metals uses recycle. gold, lead, and zinc, and a lot of those metals to be processed and provided to the industries and societies. And using these resources, then smartphones and cars will be using functional material or metallic materials, and that is also created by a group company. And also smartphones and cars, after the materials are used, then DOA ecosystem, environmental management and recycling business collects those materials, and then we'll be using them for non-ferrous metals. And this recycling business is not only for our company, group companies, but also other organizations and industries, both Japan and outside of Japan. And leaf recycling locations, we have these locations using incineration plants. We have 3 locations in Japan and 2 locations in Southeast Asia. And the 2 major ones are in Okita and Okayama prefectures. And those plants belonging to Japan Auto Recycling Partnerships, and also Akita also participates in JBRC. And now I'd like to talk about the social demands and technical challenges for leaf recycling. This is IEA's statistics about global electric vehicle sales and mineral demand estimates. Like from 2020 to 2030, 2040, the sales of electric vehicles are increasing from 20 to 30 million, and then the resources demand is also increasing. And depending on scenarios, a demand estimate can change, but in terms of lithium, demand can increase by 43 times. So based on this background, I'd like to talk about the social challenges and risk for leaf recycling. First of all, from the perspective of enhancing international competitiveness for batteries, storage batteries, we are trying to enhance our manufacturing base in Japan by 2030 and establishing the recycling system. And also lithium, cobalt, nickel, these are facing challenges for price increase and uneven distribution of resources and geopolitical risks. And our country's Economic Security Promotion Act specifies them as critical products, and trying to also increase the supply chain risk to be addressed. And there are also EU battery regulation and also the Inflation Reduction Act that are also addressing the same situation. And then we have the risk management issue that we have to think about for like ignition and explosion, and also the fire spread and corruption due to the batteries. And these are the technical challenges we are facing. Used lithium-ion batteries go through firing, burning, heating, fracturing, sorting, and they become black mass. In the usual smelting, we can't collect lithium, so we have to have the smelting process for black mass. For the dry smelting, we have this process, and for wet smelting, we do acid dissolution and extract the solvent and collect the resources. And we are facing the challenges of reducing the cost and also other things. And the used recycling is done in this manner. Basically, our focus is creating black mass. So used lithium-ion batteries, in this way, large-scale incineration plants are used to do collection and then burning and then sorting. And also, by doing the heat treatment, some of the lithium is also infused. And at QST, lithium leachate is now used for the demonstration project. And we found that we can have a high purity lithium can be extracted. Lastly, this is the expectation for LISMIC. As I mentioned earlier, for sustainable use of lithium resources, it is necessary to recover lithium from spent LIVs with high efficiency and purity. And LISMIC has great potential to technically solve this problem. In terms of technology, as explained earlier, the next generation this ion conductor, this was developed as solid electrolyte for the next generation cell element. And by using this as a membrane, we can actually collect high purity lithium. And as a recycler, we can have wet smelting and dry smelting to collect lithium from lip. And one big issue is lip structure formation can change dramatically, and black mass composition can change as well. On the other hand, when used as a electric material, high purity lithium is required. So in a smelting process, technical challenge is very high. So based on this background, in this case, LISMIC we are trying to, we are hoping that this is a technology that can address this demand for high purity so that we can have collect high purity lithium for the lithium containing solution in one through. Our company, in collaboration with QSC, we are belonging to this Alliance for Recycling of Ultra Pure Lithium Resources to collect high purity lithium. That's it from me. Thank you very much. Thank you very much, Mr. Watanabe.
続きまして
Next, we'd like to invite Mr. Hirose Kiyoshige, General Manager, Superconducting Products Department, Research and Development Division, Furukawa Electric. Mr. Hirose, the floor is yours. Thank you for introduction. My name is Hirose from Superconducting Product Department of Furukawa Electric. Thank you very much for such a valuable opportunity to me. And I'd like to extend my congratulations on the first plasma in JT60SA. I'm very delighted as one of the companies involved in the construction and very high expectations, and would like to further contribute to the fusion energy in the future as well. Today, I would like to give you a presentation about the contribution of Furukawa Electric to development of fusion energy. This is the content of my presentation. First, I'd like to talk about what kind of businesses we are doing as Furukawa Electric Group. And then I'd like to touch on some of the superconducting technology and products which made a great contribution in the nuclear energy. And in JT60SA and ITER, we'd like to give a look back on that and how we'd like to contribute in the future. A downsized small fusion reactor as well as demo TF core development on this I'd like to touch on. Furukawa Electric was founded in 1896 as a wire manufacturer. In the past, we made electric wires using copper from the Ashio copper mine in Tochigi Prefecture. Right now, we engaged in metal, polymer, photonics, and radio frequency, the four core technologies with three business segments: infrastructure, functional product, as well as electronics and automotive systems. offering a broad range of products to the world. And we have about 50 years of history related to superconducting products. In Furukawa Electric, a low-temperature superconductivity as well as high-temperature superconducting products. We are very rare companies covering both in product lineup. For low-temperature superconducting in titanium A3SN wires, and for high-temperature superconductivity, a rare earth-based copper oxide superconductive tapes are something we manufacture and sell. And in addition to what is described here for fusion, we offer products and wires for MRI and MR for accelerators in the fields of medical and analytics. We have two business bases for superconducting products. One is for low temperature superconducting wires. Nikko office, the area of foundational business, where utilized A and B and TI wires, and the copper manufacturing a office offer a high purity, a non-oxide a copper, which is required for a superconducting wires with a good performance and characteristics of the material. That is something we can show in the products. The other one is in New York City, we produced a high-temperature superconducting wires in Albany, New York State, 100 kilometers to the north from the New York City, where we create a tapes for high-temperature superconductive wires. Then I'd like to talk about our contribution in the field of fusion energy. First, it is about JT60SA. From 2008 to 2013, over 6 years, we supplied the NB3SN stranded wires with a weight of 13 tons for center solenoid, and for EF coil 36 tons, and for toroidal we supplied 43 tons of stranded wires. In total, we supplied 92 tons of stranded wires to the customer, which was significant in volume and experienced a lot in monozer Korea manufacturing. And the next one is about ITER, which we leveraged our experience. For ITER, a NB3SN stranded wires 36 tons. We supplied it from 2014 to 2017 for over 4 years. And for a superconductivity, the wires are used in the form of stranded wires in many cases, but in our company, we can cover all the process from the basic wires to the stranded wires internally. We can ensure a consistent quality for the entire process, which has been well received by our customer. And based on this contribution and records, for the demo reactor, what kind of contribution we'd like to make? That is something I'd like to touch on next. Demo reactor design, a joint team, is something we participate in as a company, and this requires larger sizes for a copper. That means there will be a significant magnetic stress, 1.4 times as large as that in ITER, applied to the coil, which means we need to ensure robustness in coil as well as a copper wires used for that, which requires a reasonable and sophisticated stranded wire design, and also it requires so many materials. We need to improve the yield for manufacturing for that reason. So in the NB3SN wires, we use this kind of materials, but outside the filament, we'd like to add composite material of copper and NB as a reinforcing material so that we can improve the strength of the wire. That is something we collaborated with Tohoku University. And the horizontal compression stress applied to the basic wire at the time of a extension of magnetics, you can see the comparison between with and without a reinforcing members. And with the reinforcing materials, you can see the critical current characteristics can be maintained even under high stress. In the future, we'd like to consider prototyping of the actual scale of conducting materials and would like to improve stranded wire characteristics and performance for a energization. That is something we'd like to validate together with the QST and Tohoku University. And for the small fusion reactor, we'd like to make contribution as well. Tokamak Energy, a UK fusion reactor startup, we have partnership with the company so that we can improve our technology. We can utilize our technology and wires to be used for a Tokamak Energy, and I would like to validate the fusion reactor. And small-scale fusion reactor requires high performance under high magnetic fields. And for that, in addition to our traditional model APs, we'd like to add a model HM as Rebco wires, and that is launched in 2021. AP was developed for conforming to various applications, covering broad range of temperature and broad magnetic fields levels. But for model HM, we developed for a low temperature from 14.0 kelvins to 20 kelvins, as well as a high magnetic fields more than 10 T. And you can see the graph compared to the traditional AP. The HM shown in blue shows better current characteristics. Together with the co-creation with Tokamak Energy, we would like to demonstrate the result for small-scale fusion reactor so that we can be engaged and accelerate the nuclear energy power generation for the small reactor. In conclusion, Furukawa Electric Group has been contributing to the operation and validation of the fusion reactor through the provision of low-temperature superconducting wires for H&J260SA as well as stranded wires. And in the future, for the demo reactor, we'd like to offer NB3SN enforced by copper NB as well as HM Rebco high-temperature superconducting wires. Through the development and manufacturing, mass production of these products, we'd like to greatly contribute to the realization of fusion energy. To realize fusion energy, we've been spent a lot of time and effort, and it will be the case in the future as well. We recognize that we need to collaborate and cooperate with so many stakeholders, and would like to hand over the technologies. And as a member of the supply chain, we'd like to make a significant step forward. We want to appreciate your continuous support. And with that, I'd like to conclude my presentation. Thank you very much. Mr. Hirose, thank you very much.
With that, we have completed technical session presentations. Before we close, on behalf of the organizer, Mr. Ejiri, the Professor Ejiri of Tokyo University, who also serves as chairperson of the annual symposium and plenary meeting organized committee in FEEFJ, would like to say a few words. Professor Ejiri, the stage is yours. Thank you for joining us today. The annual symposium started in 2012, and almost every year we have reported on the result of the international project ITER and Japan-European project Broader Approach BA and the companies that are participating in that project. And as for ITER, it has begun to take shape, and as for BA, continuous results have been achieved at Rokkasho Research Institute and others. And last year, at Naka Institute, JT60SA became operational. And we'd like to express our sincere gratitude to many companies, researchers, and policymakers who have contributed to these activities, and as well as to those many people who have supported us. And I also believe that we were once again reminded of all the support that we have received. I'd like to ask for your further contribution and encouragement. And I would also like to ask for the support and guidance for, and also the many of you young people and the student who are present here. I appreciate your contribution as well for our further development. With that, I'd like to conclude the annual symposium on ITER BA 2023. Thank you very much again for your participation, online and offline. Professor Ejili, thank you very much. And it's been a very long day, but thank you very much for attending the annual symposium of ITER BA 2023. Please feel free to leave the hall. Thank you.